Greetings everyone, welcome back to General Chemistry. Today we're going to be talking about equilibrium. In fact, we're going to be talking about equilibrium for the next few videos. This one is just going to be a basic introduction to equilibrium, and then we'll get into the real heavy math-based stuff in later videos. We will do some math today, but the main goal for today is to really just master the concept. So, without further ado, let's begin. Equilibrium. So, I've mentioned equilibrium in previous videos. I've mentioned it when talking about the concept of vapor pressure. So, it does apply to phase changes. And I mentioned it in the previous video when we were looking at reaction mechanisms. So, what is equilibrium? Suppose I start with the following reaction. Nitrogen gas reacts with oxygen gas to form 2 units of nitrogen monoxide, 2 molecules of nitrogen monoxide. So, this, of course, can happen, but it's also possible for 2 moles of nitrogen monoxide to decompose into 1 mole of nitrogen gas and 1 mole of oxygen gas. So this reaction is actually capable of going both ways. Most reactions are capable of going both ways. Most reactions that I've seen. So we can write this as 2 separate reactions. So we can say that nitrogen gas reacts with oxygen gas to form nitrogen monoxide, and we can also write nitrogen monoxide decomposes into nitrogen and oxygen. So, it doesn't really matter whether I wrote the nitrogen and oxygen on the left here and then the nitrogen monoxide on the right, or vice versa, since either side of the equation can act as the reactants and either side can act as the products. There is no true forward direction. There is no true forward direction. And there is also no true reactants and products, because nitrogen and oxygen might be the reactants of this forward reaction. Let me actually label that forward. And then this is going to be the reverse reaction if you go back to the left. So nitrogen and oxygen are considered the reactants when you're following the forward reaction, but they're the products of the reverse reaction, and you can apply similar reasoning to the nitrogen monoxide. So there are no true reactants, there are no true products, there is no true forward direction, and there is no true reverse direction. But for the sake of convenience, for ease of communication, we will continue to refer to the stuff on the left-hand side of the equation as the reactants and the stuff on the right-hand side as the products. And we'll continue with the convention that left to right is forward. So that's just for the sake of ease of communication, but know that there is no true forward, there are no true products, and no true reactants here. Okay, so when does equilibrium happen? So something that they like to show you, and I don't know how helpful it is, but something that they like to show you is a diagram that looks like this. So here they're doing a different reaction from what I have. They've got the decomposition of dinitrogen tetroxide into 2 moles of nitrogen dioxide. So you start off with N2O4, which, as you can see at the top there, is clear, colorless. And as it decomposes, more NO2 is generated, and NO2 has a yellowish brown color to it, or maybe an orange brown. And yeah, over time, more and more of the N2O4 decomposes into NO2, but not all of it. Eventually, the darkening of the color stops, and when the darkening stops and you examine what's inside of that tube, you'll notice that it's not all NO2. There is still some N2O4 that hasn't decomposed yet. Now, for the graph that they've got below, they've got concentration versus time. What they're trying to show there is the reaction rate, right? A concentration versus time graph is used to interpret reaction rates. So if you remember from last time, we used the slope of the tangent line to determine the rate, and you notice for both of those curves that the concentrations eventually just flatline. So the rate of change of concentration is the slope of a horizontal line, which is 0 after some amount of time. Once you reach that dotted line, from that point forward, the rate of the forward reaction is 0, or wait, is it? Well, not really. I'll explain that in a bit. The rate of the forward reaction doesn't actually become 0. It becomes effectively 0 due to the reverse reaction working at exactly the same rate but in the opposite direction. So, like I was saying, this isn't really my favorite way of presenting this idea. I know they put this in textbooks a lot, but students that are less mathematically inclined are usually not going to understand much from a graph like that. There is actually a second part of that graph. Hold on, let me pull it up. It was too big to fit all on one screen and be able to read it clearly, so there we go. There's the other part of it. Okay, so I basically took the graph from the bottom of that last visual I showed you. It's the same one. And then the bottom graph is new. So that one actually shows you the rates. And here you can see it more clearly that the rates of the reactions end up being equal to each other at some point in time. So what's really going on isn't that the reaction is actually stopping. It just looks like the reaction comes to a stop because the forward and reverse reactions occur in equal amounts in equal time. So it's effectively the same thing as being stopped. So let me give an example. Let's say that I'm going to use A to represent N2O4, so A is going to represent N2O4, and B is going to represent NO2. And at some point, you have a ton of NO2, I couldn't really say how much, and of course some N2O4 left over. Okay, maybe something like this. So once you've reached a state of equilibrium, what's actually happening on a microscopic level, on a molecular scale, isn't that everything just stopped reacting. You still have some N2O4s that break up into a pair of NO2s, like this, but at the same time, maybe in some other corner of the box, maybe a pair of NO2s bump into each other and form a new N2O4. And if those two things happen at the same time, or at nearly the same time, if they're happening at equal rates, then the total number of N2O4 molecules and the total number of NO2 molecules hasn't changed. So that's the basic idea behind it. It's not a static equilibrium, as you might learn about in physics. Not a static equilibrium, but a dynamic equilibrium. Static equilibrium, it's called static because you remain in the same state. of motion. That's something you'll learn about in physics if you haven't already. That's assuming that you plan to take physics at all. So this is dynamic equilibrium, not the same as static, because there is still a change going on. Things are still changing on a small scale, but if you zoom out and look at the big picture, the population of gas molecules in this container, the population numbers are stable. They stay effectively the same. So that's why we call it dynamic equilibrium. Stuff is still changing, but on a macroscopic level, you can say that the concentrations of N2O4 and NO2, or just reactions and products in general, have become constant. Okay, so with that out of the way, let me go ahead and help this idea of equal rates of forward and reverse reactions really stick in your mind. So I've written the forward and reverse reactions as two separate one-way reactions, and I can write the rate laws for both of these. Let's assume, big assumption here, but let's assume that both of these reactions are elementary. Assume that they're elementary reactions. This assumption is not a very good assumption to go with because it's not going to apply to every reaction you're going to see. I'm just using this assumption to make it easier to explain. Really, my goal here is to get the intuition. Don't trust the process I'm about to use to help you define what we will be calling the equilibrium constant. I'm just using this to give you some intuition about it. The true nature of calculating the equilibrium constant is much messier. It requires some advanced mathematical knowledge that you guys are not expected to have for a general chemistry course. But I'm just going to make this assumption to give you a simple enough example to follow. So, if these are elementary reactions, then the rate of the forward reaction, I'll just call it rate F for forward, or actually, I'll call it rate FWD because I'm going to use F for final later. Rate forward is going to be equal to some rate constant for the forward direction times concentration of nitrogen to the first power times concentration of oxygen to the first power. If it's an elementary reaction, then the exponents are just the balancing coefficients. For the reverse reaction, rate reverse, I'll just call it rate rev, is going to equal most likely a different rate constant for the reverse reaction when compared to the forward reaction. Rate constants are determined by what again? Arrhenius equation from our previous video. K equals AE to the negative activation energy over RT. So it depends on temperature, depends on activation energy, and depends on the frequency factor. Activation energies for the forward and reverse reactions are typically going to be different. The only way they wouldn't be different is if you had a reaction for which delta H was 0. And you can easily convince yourself that this is true if we go back and look at energy diagrams. Let me see. Yeah. If we go back and look at energy diagrams, if you've got the same reaction but you flip it over, so you just flip it sideways, then effectively you're swapping out an exothermic reaction with an endothermic reaction. If the forward reaction is exothermic, then the reverse is endothermic, and if it's the same reactant energy and same product energy, except you've just flipped them, then the activation energy for the exothermic direction, whether it's the forward or the reverse, is going to be lower. Because if you're going forward, then your activation energy is just from here to here. But if you're going backward, then your activation energy is from here to here. So unless delta H is 0 and the reactants and products have the same energy, then you can safely assume that the activation energies are going to be different. I can't think of any reactions off the top of my head for which delta H is 0, but if you can find one, let me know. I'd be very interested to see that because I've never seen it before. So yeah, it's reasonable to assume that K reverse is probably going to be different from K forward. And then for K reverse, the reactant is nitrogen monoxide, and we've got 2 of it. So nitrogen monoxide times another nitrogen monoxide concentration gives you nitrogen monoxide concentration squared. Okay, so equilibrium happens when these 2 rates are equal to each other. So if I set rate forward equal to rate reverse, then that is going to be the same as saying K forward times N2 times O2 equals K reverse times NO squared. And if I divide both sides by N2 and O2 and divide both sides by K reverse, then I'm going to end up with this. I'm going to end up with NO2 squared divided by N2 and O2. And then I'll divide K reverse over to the left-hand side, so I'd be left with K forward divided by K reverse. Oh, a constant divided by a constant. Well, that's just another constant. So let's call that constant big K. Okay, so big K is actually going to be the, wait, NO2? Not NO2, NO. Just NO. We're talking about this reaction. Okay, miscopied there. But as I was saying, so this constant big K, this is what we call the equilibrium constant for this reaction. Big K is called the equilibrium constant, and essentially it's equal to the concentrations of products raised to an exponent equal to the total number of moles of products divided by the concentrations of reactants raised to the total number of moles of reactants. And when I say moles, I don't mean actual moles, I mean the balancing coefficients. So let's look at this in a little bit more detail because this this doesn't tell you exactly what to do. So let's suppose I write up a completely generic reaction here. Oh, and actually before I move on, I did mention I was going to do this. I should call these the final concentrations. I should call these the final concentrations. Very, very important to note that. Final and final. Equilibrium constants can only be calculated from final concentrations. You have to wait for the reaction to at least have the appearance of having stopped. Because, again, it's dynamic equilibrium. It doesn't really stop. But you have to wait for at least the appearance of the reaction having stopped. in order to calculate the concentrations and then use them to get your equilibrium constant. So let's write a generic reaction where you've got little a moles of reactant A reacts with little b moles of reactant B. What was I doing there? And achieves some sort of equilibrium with little c moles of reactant C plus little d moles of reactant D. Okay, so if you have a generic reaction like this, and we assume all of these substances are in a state where you can calculate a concentration for them, so either aqueous or gas, solids and liquids don't count. So assuming all of these are either in the aqueous or gas phase, then you can define the equilibrium constant for such a reaction as being equal to, again, it's products over reactants, final concentrations. So it's going to be final concentration of C raised to the little c power times final concentration of D raised to the little d power, and you do this for each and every product. So if I had an E and an F, you would include those in the numerator too. Divided by final concentrations of A raised to the little a power times final concentration of B raised to the little b power. I'm probably going to forget to write final a lot because normally, and in most textbooks, in fact, pretty much every textbook I've ever seen, they don't actually write this F subscript. And I think they really should, because I see students getting confused about this all the time, using initial concentrations or concentrations from halfway before the reaction has finished, and they try to use those to calculate equilibrium constants, and it's a mess. You don't want that. You have to remember equilibrium constants are calculated from final concentrations. Once the concentrations stop changing, that's when you can calculate your big K. Okay. So yeah, as I said, solids and liquids don't count. So if you have anything in here that's a solid or a liquid, then either don't put it in this equilibrium expression at all, or just plug in a 1 in its place. Just substitute it with a 1. So for example, if I had solid calcium carbonate decomposing into calcium oxide, which itself is solid, plus carbon dioxide gas, then you can say that the equilibrium constant for this reaction is going to equal the concentration of carbon dioxide to the first power, since its balancing coefficient is a 1. So it's to the first power, final concentration, times, well, you don't need to put in anything for calcium oxide because it's solid, or you can plug in a 1 if you really have to have something there to feel comfortable, divided by, for the reactant side, we've got, well, another solid and just that, so either don't write anything in here and don't have a denominator, or if it makes you feel more comfortable to have something there, you can plug in a 1. Solids and liquids do not count. Why don't they count? I don't actually know the full reason, because you can calculate a concentration for a solid and a liquid. You can calculate how many moles they have and divide by their volume. They do occupy a volume. So, well, maybe because, and this is just me guessing, so don't take this as the official reason, but since the volume of a solid or liquid, assuming all other conditions don't change, since their volume is going to be proportional to their moles, any increase or decrease in the moles of solid or liquid isn't going to result in a change in their concentration. Maybe that's the reason. Maybe it's because their concentration doesn't change, so it would just be a constant that, I guess, just gets absorbed into the main equilibrium constant. Yeah, if you wrote it in there and it was some constant value, so you plugged in something constant over here, then you could just divide the constant over to the left-hand side, and your k divided by a constant is another constant. Call it k star. Maybe that's the reason behind it. But again, that's just me hypothesizing. I don't know the true reason. Maybe they teach you that in some higher chemistry course. I stopped after getting my chemistry minor because, well, it was multiple reasons, but probably one of the biggest reasons was I couldn't stand my classmates in chemistry. Maybe I'll talk about that in one of my rant videos in the future. But right now I have to finish this chemistry series. The students need me. Maybe. I don't know. I'd like to feel needed, but I digress. So, let's see. Oh, so we can calculate equilibrium constants based on concentrations, but for the special case of gases, we can also calculate equilibrium constants from pressures. Because, and you've seen me derive this, I think 3 times now. This will be the 3rd time. If we take the ideal gas equation, PV equals nRT, divide by volume, you get pressure equals moles over volume. Let's say that the volume is in liters. Moles over liters, that's molarity. So pressure equals molarity times RT. So you can indeed define an equilibrium constant in terms of pressure because pressure is directly related to molarity for gases. If you have a reaction that's just between gases, like what I have here, then I can get a pressure-based equilibrium constant rather than a concentration-based one. So in order to help ourselves tell the difference between which one we are using, we will sometimes call concentration-based equilibrium constants Kc, while pressure-based constants will be called Kp. So Kc is based on concentrations of products and reactants. Raised to the appropriate powers, I'll just call them x and y. While Kp is based on the partial pressures of products and reactants, assuming all of them are gases, or if you have something other than gases, liquids and solids are fine because they don't count. And pressure of reactants, and again, raise those to whatever appropriate powers. I'll just call them x and y for the sake of brevity. So let's actually go with the concentration-based equilibrium constant for this example that I had. Nitrogen and oxygen forming nitrogen monoxide. So we've got, I'll rewrite it over here. Let's do it in magenta. We haven't used that yet. At least not on this page. So Kc for this reaction is final concentration of nitrogen monoxide squared, because its balancing coefficient is 2, divided by final concentration of nitrogen and final concentration of oxygen. Okay, so that's Kc. What about Kp? So Kp for the same reaction is going to be final pressure of NO2 squared divided by final pressure of N2 and final pressure of O2. But wait a minute, we can actually expand this a bit. So since pressure equals concentration times RT, we can rewrite this as follows. We can say pressure of NO2 squared is concentration of NO2 times RT, and then all of that squared, divided by pressure of N2 is going to equal concentration of N2 times RT, and then all of that to the first power, right? These are to the first power. And then times pressure of O2 is concentration of O2 times RT, and then all that to the first power. And of course, these are the final concentrations. So if we apply our laws of exponents, then I can rewrite this as concentration of NO2 squared times RT squared. So I can write this as concentration of NO2 squared times RT squared divided by, this is going to be concentration of N2 to the first power times concentration of O2 to the first power, and then times RT from here and times RT from there, so that's times RT squared. And would you look at that, for this specific reaction, Kp is equal to Kc. Let me label those as final concentrations. So for that specific reaction, Kp is equal to Kc. But is that always going to be the case? No. In general, you shouldn't expect it to be the case. Sometimes it is, but more often than not, it isn't. So let me do the same thing I did here, but be more general about it. So I'm going to base it off of this reaction. I'm going to, first off, let's define this as being Kc, since it's based on concentration. And yeah, on a new sheet, let's take a reaction where all of these substances are gases. And let's do essentially the same thing that we did over here. Let's find Kp and rewrite it in terms of Kc. So Kp is going to be pressure of C to the little c times pressure of D to the little d over pressure of A to the little a times pressure of B to the little b equals concentration of C times RT all to the little c times concentration of D times RT all to the little d divided by concentration of A times RT all to the little a times concentration of B times RT to the little b. And if we continue expanding this, then laws of exponents say that I can distribute exponents over multiplication, or division for that matter, but multiplication is what we want to do it for this time. So I'm going to get concentration of C to the C times RT to the C times, that's going to be concentration of D to the little d times RT to the little d over concentration of A to the little a times RT to the little a times concentration of B to the little b times RT to the little b. Okay, and if I rearrange this a little bit, then I'm going to get concentration of C to the C times concentration of D to the D over concentration of A to the A times concentration of B to the B times, I'm going to put together my RTs, so you've got RT to the C times RT to the D is RT to the C plus D over RT to the A times RT to the B is RT to the A plus B. And finally, we can rewrite this as, let's see, well, what's this? What is this? This is just Kc, right? This is Kc. I forgot to write the little f's to indicate that they're final concentrations, but you can see that this is just Kc, so equals Kc times RT to the delta n. What on earth is delta n? Well, RT to the C plus D divided by RT to the A minus B would become RT to the C plus D minus A plus B. So delta n is defined as being C plus D minus A plus B. It's the change in the number of moles of gas as you go from left to right in your balanced chemical equation. That's what it is. Delta n is the change in the number of moles of gas specifically. So in the case of our example, delta n was 0, because if we go back to the original equation, you'd have 2 moles of gas in the beginning and 2 in the end. 2 minus 2 is 0. There's neither an increase nor a decrease in the number of moles of gas as you go from left to right. I guess I forgot to label these as gases, but do you really need me to label them as gases? I think we've seen these enough times to recognize them as typically being in the gas phase. So yeah, let's summarize our result here. So Kp is equal to Kc times RT to the delta n. And of course, depending on your units, you're going to want to use the appropriate value of the ideal gas constant here. And remember that T is the absolute temperature, so you shouldn't be getting any negatives. It shouldn't be in Celsius or Fahrenheit. You can also write another form of this same equation. So if you divide both sides by RT to the delta n, that's the same as multiplying by RT to the negative delta n. Remember your laws of exponents. So you can also write Kp times RT to the negative delta n is equal to Kc. I prefer that first version because, you know, avoid negatives when you can. We know how to deal with negatives, but every time you have to deal with them, there's a chance that you might forget while doing calculations, and avoiding them helps reduce your risk of making mistakes. Okay, so there we go. That's the concept of the equilibrium constant. It's some fixed. I wouldn't call it the ratio of products to reactants exactly because, you have to also consider the balancing coefficients and what powers to raise those concentrations or pressures to. But, in a sort of hand-wavy way, let's say, just for the sake of easy communication, let's just call it product to reactant ratios, even though it's not exactly that. That's just what I'll call them for convenience when I need to. So, where do we go from here? Well, let's talk about the factors that affect equilibrium. Let's talk about the factors that determine where a reaction chooses to effectively stop. So, since it's related to kinetics, since equilibrium happens when the forward and reverse rates are equal, you can imagine that equilibrium and kinetics are going to have a lot in common when it comes to the factors affecting them. Factors affecting equilibrium. Factors affecting equilibrium. So, one thing, that's not how you spell equilibrium. So, one thing that affects equilibrium is concentration. That shouldn't come across as a surprise. Concentration affects equilibrium because, well, it affects kinetics. It affects the reaction rates. So you can imagine it would have an effect on where equilibrium occurs. But you can also tell just by looking at the definitions of the equilibrium constants. You have to plug in either pressures or concentrations in order to calculate them. In order to calculate that ratio at which products and reactants just stop increasing or decreasing in quantity overall. Another factor, then, in the same vein, is pressure. Specifically when gases are involved. A third factor is going to be temperature. So, the way temperature affects equilibrium is that it affects the rate constants of the forward and reverse reactions. So, remember, rate constants are affected by temperature, according to the Arrhenius equation. So, yeah, and each rate constant is likely to be affected differently by the same temperature change. And I guess I can provide a mathematical argument for this. Do I really want to dig into this math? I mean, it's not like you need to know it, but then again, I'm the guy who always says that chemists are not mathematicians, even though they ought to be. So, yeah, let's actually dig into the math. So, I'm just going to use some numbers to make this easier to follow, because if I keep it abstract, I'm sure I'm going to lose like 3/4 of you guys. Even the ones who do like math are probably going to be lost here. So, let me draw two reaction diagrams, one for the forward and one for the reverse. So let's say the forward reaction has a diagram that looks like this, and the reverse diagram is going to have the same thing, except, backwards. So take that, and I guess that's where my peak is going to be. And then looks like I want it to stop around here. Okay, and let's just assign some arbitrary numbers here. I should label my axes, energy, and then the reaction coordinate or reaction progress or time. I'll just say time. Okay, let's say that for the, so this is going to be your forward reaction, this is going to be your reverse. And let's say over here the energy is 40 kilojoules. Let's say the energy there is 40 kilojoules, and then that would mean that this is also 40 kilojoules. And this over here, let's make that 10 kilojoules. And 10 kilojoules there. Okay, and let's take a look at the activation energy. So let's say these peaks are at, oh, I don't know, let's say 70 kilojoules. Or, you know what, 80 kilojoules. Let's do 80 kilojoules. Yeah, let's say these peaks, the activated complex or transition state is at 80 kilojoules. Okay, then the activation energy for the forward reaction is going to be from 40 to 80. It's going to be 40 kilojoules. So, activation energy forward. This is going to be activation energy equals 40 kilojoules. Meanwhile, for the reverse reaction, it's from 10 to 80, so the activation energy here is going to be 80 minus 10 is 70 kilojoules. Activation energy equals 70 kilojoules. So even if we are to assume that the forward and reverse reactions have the same frequency factor, I don't know if they would, but even if we assumed they did, then we can write the Arrhenius equation for the forward and reverse constants. Let's say, for example, that the initial temperature in kelvins is, oh, I don't know, 200 kelvins. And the final temperature, you raise it to 400 kelvins. So basically you double the temperature. Let's say for the sake of example that that's what we do. So then K forward initial is going to be some frequency factor times e to the negative, what is it, 40 over r times 200, while K reverse initial equals a e to the negative, that's going to be 70 kilojoules of activation energy over r times 200. Okay, and then for the final temperature, we can write K forward final equals a e to the negative, it's still an activation energy of 40 over r times 400 now, versus K reverse final, which is going to be a times e to the negative 70. Oh, did I write kilojoules there? I mean, I guess you can include it. I guess you can include the kilojoules, but I don't know why I did that. Maybe I just copied on autopilot there. You can include the units in your equations if you want. Usually I leave them out so I can write faster. But yeah, so you've got the forward reaction and the reverse reaction. both are going to get a boost from the increased temperature, because increasing the temperature lowers the denominator of the exponent, and lowering the denominator of the exponent decreases its magnitude, which increases the rate constant because the exponent is negative. So decreasing the magnitude of a negative exponent actually makes numbers bigger. So that part we kind of talked about before in the previous video, but there's a reminder in case you've forgotten about that. Now, these two rate constants are both going to go up when you increase the temperature, but one of them goes up more, and maybe you can tell. Let's compare. We'll leave out the stuff that stays the same, so the negative, the r, and let's assume that the frequency factor stays the same, and of course the e is the same, but let's look at the parts that change. So 40 over 200 to 40 over 400. I guess I'll do that here. 40 over 200 to 40 over 400 versus 70 over 200 and 70 over 400, going from 70 over 200 to 70 over 400. Okay, so in both cases, this ratio decreases by a factor of 2. 40 over 400 is half of 40 over 200. 70 over 400 is half of 70 over 200. So in terms of the relative change, they both decrease by 50%. Their magnitudes both decrease by 50%. But what about the absolute change? Forget about the relative change. What about the absolute change? 40 over 200 is, what is that, 0.2, I think? Let me just plug into my calculator. Yeah, it's 0.2. So you're going from 0.2 to 0.1, and then 70 over 200, I guess that would be 0.35? Yeah, that should be 0.35. Yeah. So you're going from 0.35 to 0.175. I'm not keeping with the sig fig rules here. But yeah, if we look at the absolute change, for one of them, the absolute change is greater than the other. From 0.2 to 0.1 is a change of 0.1. From 0.35 to 0.175 is a change of 0.175. So one of them decreases by 0.1, decrease by 0.1, while the other one decreases by 0.175. So they both decrease, but one of them decreases more. One of the magnitudes has its exponent decrease more, and because that exponent's magnitude decreases more, since it's a negative exponent, that means that that rate constant increases more than the other rate constant. So in this case, the reverse rate constant would increase more than the forward rate constant. And so the equilibrium position, the equilibrium constant, will have to change, because even though this conclusion that I drew over here was based on an assumption, you can still see that the rate constants do play a role in determining the equilibrium constant. So if, what did I say? The reverse rate constant increases more in this case, right? So if the reverse rate constant increases more, k forward over k reverse, if that one increases more than that one, then the ratio of forward to reverse rate constant is going to decrease overall, Both are going to get bigger, but the denominator gets much bigger. Well, I wouldn't say much bigger, but grows more than the numerator. So overall, this fraction shrinks. So you would expect the equilibrium constant value to shrink overall when increasing the temperature for this reaction. So you would expect it to shrink overall when increasing the temperature for this reaction. So in this case, if the forward reaction is the exothermic reaction, K decreases overall. K decreases when T increases, assuming that the forward reaction is exothermic, as it is in this example. Okay, so that's stuff that you don't really need to know for your typical general chemistry course, but if you care about the math and you really want to have a good intuition of what's going on, there it is. I did the math for you. We might make a callback to this later when talking about something called Le Chatelier's principle. So, concentration, pressure, and temperature. We've now established that all three of these affect equilibrium because they affect the equilibrium constant, which determines where equilibrium even is. What about catalysts? What about catalysts? I guess I'll do this in purple. What about catalysts? Catalysts do not affect the equilibrium constant. Why? I actually forgot to mention this in the previous video, but the amount of catalyst you have at the end of a reaction equals the amount you have at the beginning of a reaction. A catalyst is neither created nor consumed in the overall reaction. It's easy to see that with a heterogeneous catalyst because I think the example we showed was hydrogen and ethylene reacting in the presence of nickel. The nickel doesn't react at all. It doesn't get used up. It just serves as a space for the hydrogen and ethylene to stick to as they react with each other. Catalyst concentrations are constant. So, of course, we couldn't really define a concentration for a heterogeneous catalyst because it's typically going to be in a different phase. It's typically going to be solid or liquid. But catalyst concentrations for homogeneous catalysts, to be specific, remain constant. For heterogeneous, they're not going to count towards the equilibrium constant anyway, but for homogeneous catalysts, their concentrations are going to remain constant. If I go back to the reaction mechanism for catalyzed decomposition of hydrogen peroxide, which I've got right here, so you might remember this from last video. The homogeneous catalysts were the hydrogen and bromide ion, or hydrobromic acid in general. If you use up 2 moles of hydrobromic acid in step 1, but then you produce 2 moles of hydrobromic acid in step 2, then overall the concentration of hydrobromic acid hasn't changed. You give back whatever you use. So the final concentration equals the initial concentration. So even if you wanted to include it in the equilibrium constant, even if you wanted to include it in a generic concentration-based equilibrium constant, the amount of catalyst you have on the product side is going to equal the amount of catalyst you have on the reactant side. In fact, in the overall reaction, it's not supposed to show up at all, but just for the sake of argument, let's say you did include the catalyst, you'd have to show it on both sides of the equation, so it would be a reactant and a product at the same time, and its concentration would be the same at the end as it is at the beginning, so it just cancels out. Maybe not the most legitimate of arguments, but for intuition's sake, I think this can help you believe that catalysts don't affect where equilibrium is. Does that mean catalysts are useless? No, not really. Catalysts still have a role to play. They don't affect where equilibrium is, but they do affect how quickly you get there. The catalyst speeds up the forward and reverse reactions at the same time by the same amount, so the place where the forward and reverse reactions reach a tie in terms of speed is still going to be the same, but they are faster at getting there. They do get there sooner. But as a general rule, catalysts do not affect the position of equilibrium. They do not affect equilibrium constants. All right. Let's talk about something known as the reaction quotient now. Now let's talk about the concept of the reaction quotient. Reaction quotients. And let's pit them against equilibrium constants. Reaction quotients versus equilibrium constants. This is something that students get confused about all the time. And I think part of the reason is, and I might be wrong about this, but I get the feeling that teachers don't really go out of their way to thoroughly explain the difference. They just kind of put it in front of students and expect them to know, and you can argue about whether or not it's reasonable to have those expectations, but the fact of the matter is students aren't getting it, so you really do need to explain it. So if you have a teacher that doesn't bother to explain these things, ask them nicely to start doing that, and if they don't respond to you asking nicely, then, I don't know, complain about it on Twitter or something. Or contact your school board. They'll probably change something. Who am I kidding? They'll change nothing. If their job is to just sit down and make money doing nothing all day, then why would they actually put in the work and seriously think about how to make the curriculum work better for students? I'm sorry, I'm getting too political here. I'm sure there are good school boards out there. I mean, it's not necessarily the school board's fault, it's the people who get in there. Some of them are among the laziest and most corrupt people ever. Reaction quotients versus equilibrium constants. So, reaction quotients, the reaction quotient Q, is given by the following formula. We're going to use the same generic reaction that we've been using. Let's say this is our reaction. It doesn't matter if they're gases or aqueous. So the reaction quotient is calculated like so. Wait a minute. Isn't this the same as the equilibrium constant? So that's the point of confusion that teachers don't actually elaborate on. Remember how I've been emphasizing that Kc is about final concentrations, or Kp being about final pressures? Well, Q is the same thing, but it's not final. Well, it could be final, but it doesn't have to be. So the reaction quotient gives you the current product to reactant concentration or pressure ratios. You can call them QC and QP, depending on whether they're based on concentration or pressure if you want, but most of the time we'll just call it Q without a subscript. And it'll be understood which version you need to use because you'll typically be given an equilibrium constant to compare it against. So if you're given a concentration-based equilibrium constant, then you'll use a concentration-based reaction quotient. And if you get a pressure-based constant, you use a pressure-based quotient. So usually we don't even bother with subscripting Q, but you can if you want to. So yeah, if I have a reaction and it has a certain equilibrium constant to it, let's say, for example, just for the sake of example, I'll make up a number here. Let's say that the equilibrium constant for the combination of nitrogen and oxygen to form nitrogen monoxide, let's say that the equilibrium constant for that is 16. Let's say that N2 plus O2 forming 2NO. Let's say that for this reaction, K is equal to 16. Okay, then if I have a reaction and I start with, let's suppose I have a container and I start with, let's say I start with, and I'm going to express this in terms of concentrations, let's say I start with 3 molar of nitrogen and 2 molar of oxygen inside of a container, and there's no nitrogen monoxide. Okay, then I can calculate the reaction quotient for this. Q equals, what was it? So it's going to be concentration of nitrogen monoxide to the second power over concentration of nitrogen times concentration of oxygen. Okay, well, how much nitrogen monoxide do I have? Right now, 0. So 0 squared over 3 times 2 over 3 times 2, 0 over 6, which of course is 0. Okay, so the current product to reactant ratio, or the current reaction quotient, is 0. Once equilibrium is reached, the reaction quotient will be equal to the equilibrium constant. It'll be 16. So 0 is where you're at right now. 16 is where the finish line is. So you need to go from 0 to 16. Well, how do you do it? There's only one way to go. If all you've got is nitrogen and oxygen, then you can't form more out of nothing. So the only way you can go is forward. The only way you can go is form nitrogen monoxide. And so you start forming some nitrogen monoxide. Let's say I eliminate 1 nitrogen here and 1 oxygen here, and that produces 2 molars of nitrogen monoxide. Okay, what's the reaction quotient now? Let's call this Q0, and then the next reaction quotient, let's call that Q1. So now Q1 is going to be nitrogen monoxide squared, so that's going to be 2 molar squared, divided by, we've got 2 molar of nitrogen gas to the first power, and oxygen to the first power, we've only got 1 molar left. So that's going to be 2 squared is 4 over 2 times 1 is 2. Okay, so now the reaction quotient is 2. Are we at 16 yet? No, we're not, so the reaction isn't done yet. The reaction is going to keep on going until the reaction quotient is equal to the equilibrium constant. Which way is it going to have to go now? Well, 2 is lower than 16. You are below the number you need to be at, so you need to increase the reaction quotient. How do you increase it? Well, the numerator is based on products and the denominator is based on reactants. If you want to increase this fraction, you need to increase the numerator and or decrease the denominator. That would make the number larger. Increasing the numerator, increasing products, decreasing the denominator, decreasing reactants. You decrease reactants and increase products by continuing to go forward. And that's really all there is to it. So Q tells you where you're at, K tells you where you're going. As long as you remember that, you should be fine. Teachers don't really go out of their way to explain it, at least not in my experience. So there it is. As long as you can understand that and really wrap your head around it, you should be fine with your whole Q versus K stuff. So yeah, products are going to continue increasing, reactants are going to continue decreasing until you reach 16. I could go ahead and calculate what the final concentrations would have to be for this to happen, but we'll be doing problems like that later on, so for now we'll just skip on that. For now, I just want to summarize what we can conclude from different Q versus K comparisons. So if Q is less than K, reaction proceeds forward. Reaction would have to proceed forward in order to reach K. If Q is greater than K, this can happen if I started with more product than reactant, or even if I started with no reactant at all. If I started with a box full of mostly nitrogen monoxide, and maybe some nitrogen and oxygen in there, then my reaction quotient would start way above 16, and I would need to lower it. I would need to decrease the numerator, decrease the products, and increase the denominator, increase the reactants. And that's done by going in the reverse direction. So the reaction would have to go in the reverse direction if Q is greater than K, and if Q is equal to K, well then you are at equilibrium and everything effectively stops. Remember, it's dynamic equilibrium, so it doesn't really stop, but it effectively stops. And there is a video that I will link to in a pinned comment. I guess I'd put it under the other notes section, that has a rather amusing example of equilibrium. Something about arm faces and handless people. You'll get it when you see the video. It's somewhat amusing, but the most important thing is that it kind of helps illustrate the point. So I'll link to that video, and you can go ahead and watch it. Maybe pause this video and watch it and then come back. It's not that long. Not compared to my videos anyway. So that's Q versus K. What else? So before we look at problems, there's one more thing, which is the magnitude of K. The magnitude of K can tell you a lot. The magnitude of K can tell you a lot. So the equilibrium constant tells you where equilibrium lies. If the equilibrium constant is noticeably larger than 1, versus if it's nearly equal to 1, versus if it's noticeably smaller than 1. Each of these tells you something different. So each reaction is going to have different equilibrium constants, and even for a single reaction, it's going to have a whole bunch of equilibrium constants depending on what the temperature is. But some reactions, even if you adjust the temperature a lot, they will tend to favor products, and some reactions will tend to favor reactants. And some reactions tend to favor products and reactants equally or nearly equally. So what do I mean by that? If the equilibrium constant is large, for example, let's say we had K equals 3.0 times 10 to the fourth. Well, this tells me that once you take the ratios of final concentrations of products and reactants, once you take their quotient, once at equilibrium, the numerator is going to be way, way larger than the denominator. You're going to have way more products at the end than reactants. So maybe after you finish the reaction, 95% of what's inside that container is going to be products, and only 5% will still be reactants that haven't turned into products. If K is significantly less than 1, so for example, if you had K equals 1.5 times 10 to the negative 3. Well, this is a small number, so this tells you that your products over reactants is going to be rather small, indicating that you either have very few products or you have a lot of reactants. Either way, you're going to have more reactants in that vessel than products. We've seen this before. We talked about it 2 videos ago. Incomplete dissociation, weak electrolytes. So if I have something like acetic acid, CH3COOH, some of it decomposes into acetate ion and the hydrogen ion. Some of it ionizes, but not all of it. And that should have a negative around it, and then plus the hydrogen ion. So some of your acetic acid will break down into acetate ion and hydrogen ion, but most of your acetic acid molecules are going to stay intact. Most of them are going to stay intact, so you're going to have less product at the end than reactant. And so once equilibrium is reached, you can imagine the ratio is going to be really, really small if it's products over reactants. And of course, when K is around 1, maybe not exactly 1, but somewhere near 1, then it won't be exactly 50-50 most of the time, but it won't be overwhelmingly products or overwhelmingly reactants. Like the populations of reactants and products in your reaction vessel are going to be pretty comparable to each other. There is no clearly dominant species inside your vessel if the equilibrium constant is nearly 1. Speaking of things being inside a vessel, I should have brought this up earlier, but it doesn't make sense to talk about equilibrium in an open container for a lot of reactions, because what if I had, going back to my same example, what if I had nitrogen and oxygen, I pumped a bunch of it into a container, but the container was left open. So, I break open this wall, for example, for the gas to escape. Well, then in that case, you're never going to reach equilibrium, because even if you can get your nitrogens and oxygens to run into each other before coming out of the vessel, you'll make some nitrogen monoxide and then it'll fly out. It'll just go into the atmosphere. And if it goes into the atmosphere, well, now it's not really confined to a space unless you want to calculate the concentration of nitrogen monoxide by taking the moles that you generate divided by the volume of the entire atmosphere. If you're willing to do that, then I guess you can calculate the equilibrium pressures or concentrations, but yeah, it's pretty much a fool's errand at that point. So you do need to have a closed container. You do have to confine your reactants and products to a certain volume. Otherwise, you can't really get concentrations for them. And even if you could, there's the other problem of they're escaping your system. So if you have a certain ratio of nitrogen monoxide squared to nitrogen times oxygen that you're trying to achieve, if you're trying to reach a certain K value, you'll never reach it because this number will never climb high enough. It'll always decrease back down to 0 as nitrogen monoxide gets out of your vessel. And eventually you're just going to run out of nitrogen and oxygen. So if you wanted to actually use up all your nitrogen and oxygen and you didn't want to have any left, then you would actually on purpose leave an opening in the container to let the nitrogen monoxide out so that an equilibrium can never be reached. You're not going to have a reverse reaction if you don't keep the product molecules in there to actually do the reverse reaction. So that's just a comment I wanted to make. Equilibrium typically needs to happen inside of closed containers. You typically want to have a closed system for equilibrium. Okay, let's look at some problems. Number 1, or well, sheet 1, I should say, or slide 1, whatever you want to call it. Okay, number 6, explain why there may be an infinite number of values for the reaction quotient of a reaction at a given temperature, but there can be only one value for the equilibrium constant at that temperature. We've already explained this. Reaction quotient you can calculate at any point in the reaction. At the beginning, halfway before it's done, a third of the way before it's done, when it's done, 500 years after it's done. You can calculate a reaction quotient at any point in the reaction. And you'll get different values each time, unless, of course, it's already done, in which case you'll just see after calculating it a couple times that it isn't changing anymore, and then you'll know you're at equilibrium. But there's only one finish line. There's only one equilibrium constant for any given reaction, for any given temperature. Number 7, explain why an equilibrium between bromine liquid and bromine gas would not be established if the container were not a closed vessel as shown in the figure, which I don't have. Well, we just talked about this. It needs to be in a closed container because if you let the bromine gas escape out of an opening in the container, then you don't have the reverse process of bromine gas turning back into bromine liquid anymore. It can't happen if there's no gas in the container, if it all leaves. So we just talked about that. And number 8, if you observe the following reaction at equilibrium, is it possible to tell whether the reaction started with pure nitrogen dioxide or with pure dinitrogen tetroxide? No. If it's at equilibrium, you cannot tell whether you started with a bunch of NO2 and some of it turned into N2O4, or if you started with a bunch of N2O4 and some of it turned into NO2. If you're looking at the final state, there's no way to tell which direction it came from. Again, there's no true forward direction, so you can get to equilibrium from either side depending on what you put in there, but you can't backtrack because of that. Number 9, among the solubility rules previously discussed is the statement all chlorides are soluble except for mercury 1, silver, lead 2, and copper 1 chloride. Copper 1 is news to me. I knew about the other 3, but You learn something new every day, I guess. Copper 1 chloride is not soluble. Good to know. Well, we shouldn't say not soluble. We should say very, very, very low solubility. So part A, write the expression for the equilibrium constant for the reaction represented by the equation. Same thing for part B. And it wants us to explain whether the equilibrium constant is greater than, less than, or nearly equal to 1. Okay, we can go over this real quick. It's not as hard as it sounds. So this is all about the magnitude of K. So if I have AgCl solid, and you put it in some water, and you get Ag plus in the aqueous state plus Cl minus in the aqueous state, what is the equilibrium constant expression going to be? So the expression is just, the formula for calculating it without necessarily producing the actual number. So the equilibrium constant expression is going to be K equals concentrations of products over concentrations of reactants, not counting liquids or solids. So that's concentration of silver ion to the first power times concentration of chloride ion also to the first power, divided by, well, there's nothing to divide by. You can plug in a 1 if you want, but solid AgCl doesn't count. So there's your equilibrium constant. Do we expect it to be less than 1, greater than 1, or nearly equal to 1? Well, we already know silver chloride isn't very soluble in water, so if you put in a big chunk of AgCl, even in a bucket of water, not much of it is going to dissolve, so I'm not expecting to have a whole lot of product. The concentrations are going to be really, really tiny, like probably thousandths, if not millionths, or even billionths of a molar in terms of concentration. Very low solubility, so I would expect K to be rather low. I would expect K to be less than 1. You don't make a lot of product in this sort of process. Okay, similarly, they had same thing with lead 2 chloride. I guess we can do that. Only thing that changes is the expression. Lead 2 chloride starts out as a solid. Some of it, in fact, very little of it, is going to give you lead 2 ion plus 2 chloride ions. And since it's 2 chloride ions instead of 1, we can say the equilibrium constant expression is going to be concentration of lead ion times concentration of chloride squared. Times concentration of chloride squared. And you can divide that by 1 if you want. There's nothing aqueous or gaseous on the left-hand side of that chemical equation. And again, I would expect K to be less than 1, a whole lot less than 1. It's not going to be negative. That isn't going to make sense. You're never going to have negative equilibrium constants, but something way, way less than 1 nonetheless. A really, really small fraction. Okay, what else do they have for us? Number 10. Among the solubility rules previously discussed is this... Oh, same as number 9. Okay, we can skip that. Let's take a look at the next sheet. See if there's anything worthwhile there. Benzene is one of the compounds used as octane enhancers in unleaded gasoline. It is manufactured by the catalytic conversion of acetylene to benzene. And there's the equation for it. Which value of Kc would make this reaction most useful commercially? Okay, so if I'm a manufacturer and I want to use benzene to enhance my gasoline, then I'm going to want to produce as much benzene as I possibly can in my reactions. So I would want a process where when it stops, when it reaches equilibrium, most of what's inside of my reaction vessel is going to be the stuff I want, the benzene. So I want more product than reactant, hopefully overwhelmingly more product than reactant. I would want Kc to be 10 because 10 is higher than 1. It's the highest out of the 3 choices that they've given us. So yeah, I'd want the equilibrium constant to be high. More products at the end if equilibrium constant is high. Okay, number 12, show that the complete chemical equation, total ionic equation, and net ionic equation for the reaction represented by Ki plus I2 gives Ki3 give the same expression for the reaction quotient. Ki3 is composed of the ions K plus and I3 minus. I'm not entirely sure what they're getting at here. The complete chemical equation, the total ionic, and the net ionic. Okay, let's try and see what this is trying to get at. I'm not really sure what they want, but let's write the 3 equations. They already gave us one. So we've got Ki aqueous plus I2 aqueous yields Ki3 aqueous. The total ionic equation, potassium iodide, is the same as potassium ion plus iodide ion. Plus iodide ion. So there's our total ionic equation. And if I split that up, that's going to be K plus. And as they told us, that's going to be I3 minus, all in one ion. And then for the net ionic equation, I would just eliminate the K plus, and that would leave us with I minus plus I2 produces I3 minus. That would be our net ionic equation. If you don't remember what total and net ionic equation means, then go back to video number 4, because that's where we explained that. If you're taking AP Chemistry, you definitely want to make sure you know how to get net ionic equations, and I think I recommended back in video number 4 that you get better at kind of jumping straight from the balanced equation to the net ionic equation. If you practice it enough, you can get from here to here without having to write this out. And you'll be able to do it in seconds. So it's definitely worth practicing, because on the AP exam, and I think on the IB exam, though I'm less sure about that one, they do expect you to write net ionic equations on the free response section anytime they ask for an equation for your answer, a chemical equation. Okay. So let's go ahead and write the equilibrium constant expressions for each of these. So for this one, K is going to equal concentration of Ki3 over concentration of Ki times concentration of I2, all to the first power because their balancing coefficients are 1s. For the total ionic equation, I guess I'll call it Kc so that we don't confuse it with potassium. Kc is going to be concentration of K times concentration of I3 minus over concentration of reactants. We've got K, I minus, and I2. Okay, and then for the net ionic equation, we've got Kc is equal to concentration of I3 minus over concentration of I minus and concentration of I2 at equilibrium, so the final concentrations. I know I'm starting to sound like a broken record, but you'll thank me later. It's that important to remember. K is about final concentrations. Okay, so they want us to show that these three values are the same. Okay, now I see what they want. Okay, so it's easy to prove that these two are the same because all you have to do is cancel out the K plus concentration. The spectator ion doesn't really participate in the net ionic equation. Its concentration at the end equals its concentration at the beginning. It just cancels out. So you can see why these two expressions are equivalent to each other. So now, why is this the same as this? Or effectively also this. I'll just compare these two because there's less stuff in there. Why are these the same? Well, because the concentration of I3 minus is equal to the concentration of Ki3. For every 1 molar of Ki3, you have 1 molar of I3 minus. If this concentration was 2 molar, this concentration would be 2 molar. You'd be getting 2 molar of this and 2 molar of potassium ion. And the potassium ion, as we said, cancels out, so it doesn't matter. So yeah, concentration of Ki3 equals concentration of I3 minus. In the same vein, so we know this and this are equal to each other. We already have concentration of I2 is the same. Concentration of Ki equals concentration of I minus for the same reason. If I had 3 molar of Ki, then it would break up into 3 molar of K plus and 3 molar of A minus. And the K plus, of course, like we said, cancels out. So yeah, 3 molar becomes 3 molar. It's the same concentration for I minus as you have for Ki. And that's why all three of those are equivalent. Okay, so I guess that problem wasn't as weird as I thought it would be. Number 13, for a titration to be effective, the reaction must be rapid, and the yield of the reaction must essentially be 100%. Is Kc greater than 1, less than 1, or approximately 1 for a titration reaction? It's going to have to be not just greater than 1, but way, way, way greater than 1, so that the final concentration of products over final concentration of reactants is so high that there's practically no reactants in there. So yeah, for reactions that go to 100% or nearly 100% completion, you can think of them as being the same as reactions with really, really high equilibrium constants, really heavily favoring products by the end of the reaction. 14, for a precipitation reaction to be useful, the product of the reaction must be insoluble. So, yeah, that's basically the reverse of 13. We already did that with the silver chloride and lead 2 chloride problem earlier. Since the solubility is supposed to be really low for a precipitate, you would want a really, really low equilibrium constant, less than 1. Okay, what else do we have here? Write the mathematical expression for the reaction quotient for each of the following reactants. Okay, I'm not going to do all of these. I'm just going to do some just in case we haven't seen enough examples of it. So first reaction we've got there, CH4 plus Cl2 gives you CH3Cl plus HCl. Or if you want the names, carbon tetrahydride, also known as methane, plus chlorine gas yields chloromethane. We will learn the naming rule for compounds like that in video number 19, plus hydrochloric acid. So yeah, concentration of chloromethane times concentration of hydrochloric acid divided by concentration of methane times concentration of chlorine. I guess I should write it out because that can be confusing in words. Let's write it out. I'll do it on a new sheet. So it's going to be Q equals CH3Cl. Concentration or pressure, since these are gases, you could also use pressure if you wanted. But I'm just going to use concentration. Oh, by the way, speaking of pressure, let me comment on. So when I wrote the equilibrium constant and or reaction quotient in terms of pressure, I used a capital P, but another notation you can use is just parentheses. I think P is easier to write, but you can do this. You can do the substance in parentheses, and that means pressure of, the same way that putting the substance in square brackets means concentration of. So I guess I'll call this QC and call this QP. Over, what were the reactants? Methane and chlorine. CH4 and Cl2. So yeah, you can use parentheses here. I wouldn't, because I think it's faster to just write it this way. P of CH3Cl times P of HCl over P of CH4 times P of Cl2. This is the way I'd prefer to write it, especially because not everyone is going to know that parentheses mean pressure. But if you see that, just in the event that you see that, that's what it means. If you see parentheses instead of brackets, it's pressure, not concentration. And if you're one of those students that can't be bothered to draw proper square brackets and you settled for parentheses before, well, you can't get away with that anymore because it means a different thing. Okay, let's look at another one. B, would you look at that? It's the example that I've been using for the greater part of this video so far. Nitrogen plus oxygen giving nitrogen monoxide. We'll skip that. We've seen it enough times. Ooh, let's do 15G. Let's do 15G. Okay, so we've got CH4 plus O2 giving CO2 plus H2O. The H2O is liquid, so it's not going to count. Okay, in that case, since they're all gases, I can define a QP. I'm just going to settle for a QC. So I'm going to go with let's see, it's going to be concentration of CO2 to the first power over concentration of CH4 to the first power. And then oxygen has a coefficient of 2, so it's going to be times oxygen concentration to the second power. Nothing too hard there. Okay, and you can play around with the rest of these on your own. It's not that hard. I would still recommend going through these even though they're not that hard because, you know, you want to develop the habit. If you make it a habit, if you practice it enough that you can sort of do it on autopilot, that'll save you time for those problems that require more thinking. If you exhaust yourself thinking too hard about even the simpler problems, then you're not going to have a fun time with the trickier problems. Let's go ahead and look at our next set. Anything interesting here? The initial concentrations or pressures of reactants and products are given for each of the following systems. Calculate the reaction quotient and determine the direction in which each system will proceed to reach equilibrium. Okay, so we kind of did an example of this, but let's go ahead and do one of these. Let's do A. So we've got the decomposition of ammonia. Decomposition of ammonia. And they've given us Kc is 17, the concentrations at some point in time, not necessarily at the finish line, are 0.2, 1, and 1 molar for ammonia, nitrogen, and hydrogen respectively. Okay, let's plug those numbers in and see what we get. Not too hard to do at all. So the products are nitrogen and 3 hydrogen, so I'm going to do Q equals nitrogen times hydrogen cubed divided by the reactant is ammonia, and we've got 2 of it, so that's going to be ammonia squared. They're all gases, so they do have a concentration. They do contribute to the reaction quotient and the equilibrium constant. Plugging in the values, we've got, let's see, 1 for nitrogen and 1 for hydrogen. 1.00 times 1.00 cubed over ammonia. We've got a concentration of 0.2, so that's going to be 0.20 to the second power. Let's see what that gives us. So 1 times 1 cubed is still 1, divided by whatever 0.2 squared is. I guess that would be 0.04, so 25, right? 1 over 0.2 squared. Yeah, it's 25. And that is 2 sig figs, so yeah, it works. Okay, so Q is equal to 25. K is equal to 17. So if Q is at 25, that means you're too far to the right. Q is too high. This reaction is too far right. In order to get to equilibrium, it needs to head left. You need to go in the opposite direction. You need to go from nitrogen and 3 hydrogen to 2 ammonia. You need to use up some of your nitrogen and hydrogen and create some new ammonia in order to reach equilibrium. And that's basically how it goes down. All of those problems are good to use as examples. You'll probably run into 1 or 2 where Q is already equal to K. At least that's what I'm expecting. I haven't done all of these ahead of time, so I wouldn't know, but if they're good at writing textbook questions, then they really should have a couple of those, just so you can have an example where Q is already equal to K, and the reaction's already at equilibrium. But I don't know if you're going to see that. Don't be surprised if you do, is all I'm saying. Let's take a look at our next sheet. So the following reaction has Kp equals 4.50 times 10 to the negative 5 at 720 kelvins. And it's the formation of ammonia this time. If a reaction vessel is filled with each gas to the partial pressures listed, in which direction will it shift? Okay, we already did that. We did it with concentration, but same deal. Calculate Q, compare it to K. If Q is too high, shift to the left towards making more reactants, and if Q is too low, shift to the right towards making more products. 20, determine if the following system is at equilibrium. Again, calculate Q and compare it to K. Nothing new there. 21, which of the systems are homogeneous equilibria and which are heterogeneous for problem 15? Okay, so homogeneous equilibria are equilibrium equations where everything counts towards the equilibrium constant. So everything is either aqueous or gas. If you've got solids or liquids in there, then it's a heterogeneous equilibrium. And that's basically the gist of it. It's just that simple. Homogeneous as in part of a homogeneous mixture. Can be part of a homogeneous mixture, or in other words, a solution. Aqueous substances are, by definition, in a solution of water, or in a solution with water as the solvent, I should say. And mixtures of gases are always homogeneous mixtures, so they count as solutions as well. Okay, so that's 21 and 22. 23, for which of the reactions does Kc equal Kp? And they're asking the same thing for 24. We already showed an example where Kc is equal to Kp, so let's review that real quick. Our formula was Kp is equal to Kc times RT to the delta N. If delta N is 0, RT to the 0 is going to be 1. So Kp equals Kc times 1 if delta N is 0. If the number of moles of gas on the right-hand side equals the number of moles of gas on the left-hand side. So I guess we can go back and look at some of those equations real quick and compare the moles of gas. I think they were talking about 15 and 16 here. Okay, so 15A, we've got 1 mole of CH4 plus 1 mole of Cl2 forms 1 mole of CH3Cl plus 1 mole of HCl. So that's for 15A. 2 moles of gas on the right, 2 moles of gas on the left. Difference is 0. Same thing for B. You've got 2 moles of gas on the right and 2 moles of gas on the left, 1 for nitrogen plus 1 for oxygen. So that's a delta N of 0. So in that equation, Kp is going to be equal to Kc. For 15 part C, we've got 2 sulfur dioxide plus oxygen gives you 2 sulfur trioxide. Okay, so we've got 2 moles of gas on the right and 3 on the left. Delta N is -1, so not 0. So in that case, Kp and Kc are gonna be different. And yeah, just follow that same pattern. Part D, you've got 1 mole of gas on the right, no gases on the left. Delta N is +1, and so on and so forth. Find the ones for which delta N is 0, and those are going to be the ones where Kp equals Kc. Nothing too hard there. What else do we have on this page? Just did 23 and 24 essentially. 25, convert the values of Kc to values of Kp, or vice versa. Okay, so that's really just plugging into the equation. Let's do one of these. Let's do 25. Let's do number 25. So we've got Kc equals 0.50 at 400 degrees Celsius. We need to convert that to kelvins. So let's see here. We're given Kc equals 0.50 at 400 degrees Celsius, which equals 673 kelvins. I guess I'll put that in parentheses. So yeah, first let's find our delta N. So the equation was N2 plus 3H2 gives us 2NH3, and all of these were gases. So we've got 2 moles of gas minus 1 plus 3 is 4 moles of gas. 2 minus 4 is negative 2. Delta N equals negative 2. This is an exact number, by the way, so it shouldn't affect your sig figs. So then we've got Kp is equal to Kc, which is 0.50, times RT to the delta N. In this case, I want my ideal gas constant to be atmospheres and liters, so 0.08206 times 673 kelvins, and then all that to the negative 2. Equilibrium is the part of chemistry where teachers start becoming less strict about the sig fig rules. And the reason for that is because I think a lot of them don't know the sig fig rules for dealing with exponents, and you deal with that a lot. I kind of talked about it in the previous video a little bit. I think there was one example that I did dealing with sig fig rules of exponents, but let's talk about it again. So no, I think I did it for logarithms. This is going to be the reverse process. So if you raise something to an exponent, then the number of sig figs in the result, once you raise something to an exponent, should equal the number of decimal places of the exponent itself. And since this is an exact number, you actually have infinite decimal places, so not going to have an effect on that. We've got 4 sig figs times 3 sig figs is 3 sig figs raised to an exact number. Oh, actually, what is the rule if the base doesn't have an exact value? I'm not too sure about that. Well, we'll stick with 3 sig figs because that's probably what most people are going to do when they don't know any better. And we're going to end up with 2 sig figs in the end anyway, so why not? 0.08206 times 673. Okay, raise that to the negative 2. Well, actually, wait. Round it to 3 sig figs first. So that's 55.2 raised to the negative 2. Round that to 3 sig figs, so that's 0.000328. 0.000328 times 0.50. Rounded to 2 sig figs, that's 0.000164, or in scientific notation, rounded to 2 sig figs, it's 1.6 times 10 to the negative 4. And there we go. Okay, you can handle the other ones on your own. In some cases, they'll give you Kp, in which case you divide by RT to the delta n, or multiply by RT to the negative delta n. You can choose which one you prefer based on how confident you are in your math skills. But yeah, that's problem 25. That's how you go about it. Nothing too hard to do, just use the equation. 26 appears to be the same as 25. 27, what is the value of the equilibrium constant expression for the change H2O liquid to H2O gas at 30 degrees Celsius? See Appendix E. Okay, so I haven't looked at Appendix E, but I think I know what they're getting at. They want you to use the vapor pressure at 30 degrees Celsius. So I'm going to use the appendix of a different book since that's what I have in front of me right now. And let's look up the vapor pressure of water at 30 degrees Celsius. So I guess I can rotate the camera for you guys so you can have a look at what I'm doing. So this gives me the vapor pressure in torrs. I'm probably going to want to convert that to atmospheres. Vapor pressure of water at 30 degrees Celsius is 31.82 in torrs. 31.82 at 30 degrees Celsius. Okay, let's bring our camera back. Is that lined up right? Yeah, that looks about right. Wait, does it? No. Okay, that's better. Now we're back in business. So, I know that the pressure of water vapor at 30 degrees Celsius is equal to 31.82 torrs. If I divide that by 760, 31.82 over 760, that's equal to 0.0419 atmospheres. Actually, wait. Is it an exact conversion between torrs and atmospheres? It doesn't say. I'm going to assume that 760 is 3 sig figs and just be on the safe side, round it to 0.0419 equals 0.0419 atmospheres. Gonna round to 3 sig figs to be on the safe side. Okay. Now then, the equation they gave us was liquid water turning into water vapor. In a sealed container, the pressure of the water vapor would build up to 0.0419 atmospheres, and then at that point, the evaporation would stop until you either raise the temperature or open the container and let the water vapor out so that more H2O liquid can evaporate. So equilibrium constant is just equal to the pressure if you're calculating Kp. If you're just calculating Kp, then that's just equal to the pressure of gas, 0.0419, over the pressure of reactants. It's liquid, so you can't really... Well, you can define a pressure for it, but that's more of a physics thing. And you have to know, like, at what depth are you measuring the pressure of the liquid. Okay. So yeah, if you want to convert that to concentration, you can. It wouldn't be that hard. Delta N is just 1, so just multiply by RT. That's all you have to do. Where do we want to go from here? Is there anything else on this sheet that I want to do? Write the expression of the reaction quotient for the ionization of cyanic acid in water. And yeah, that's simple enough. We know how to do it. So I don't think we need to cover it. 29, same thing. Ionization of NH3 in water. Yeah, as long as you know what chemical equation to write, it shouldn't be too hard to come up with. If you don't know how to do it, don't worry. We'll cover that in the next chapter, which covers acids and bases. Pretty much all of those equations are going to be things ionizing in water. Number 30, what is the approximate value of the equilibrium constant Kp for the change given at 25 degrees Celsius, and the equilibrium vapor pressure for this substance is 570 torrs. Okay, so same thing we did with problem 27. And yeah, just like with problem 27, we only have 1 mole of product, so just raise it to the first power, which means don't change it at all. And Kp is just equal to the vapor pressure. I would convert it to atmospheres, but I guess you can keep it in torrs as well. Units for the equilibrium constant, now that I'm thinking about it. There are no official units for equilibrium constants. Even though you calculate them from molarities or pressures in atmospheres or torrs, equilibrium constants don't really have official units, because sometimes you're going to have higher exponents on the numerator than the denominator. Sometimes it's going to be higher exponents on the denominator than the numerator. And keeping track of all that and giving it in units of molarity squared, or molarity to the -2, or molarity cubed, or whatever, or sometimes getting all of your concentration or pressure units to cancel out between the top and bottom, and just having no units at all. It's messy, and there's not much point to knowing the units of an equilibrium constant, so we just keep them unitless regardless of what the units work out to mathematically. So yeah, we don't define any official units for K. We don't need them. Was there one more I wanted to go over before we talk about Le Chatelier? No, I think that's it for that stuff. Okay, let's talk about Le Chatelier's principle now. Let's talk about an infamous idea. Well, I shouldn't say infamous, but a big idea in chemistry called Le Chatelier's principle. And I'm probably going to spell this guy's name wrong. Le Chatelier's principle. I forget if there's an E at the end. There might be an E after the R. Le Chatelier's principle. Okay, so this is another thing that students often get confused about. Le Chatelier's principle applies to reactions that are already at equilibrium, and then you just mess with them and you disturb the equilibrium, and they're not at equilibrium anymore, and they're going to do something to regain their equilibrium. So Le Chatelier's principle only applies to something that was at equilibrium, and you just did something to it to knock it out of its equilibrium state. If it's not at equilibrium already, then Le Chatelier's principle does not apply, and I forgot to cross that T. Le Chatelier's principle only for a system at equilibrium. Basically, what Le Chatelier says, and they try to make it intuitive and try to help you figure out what's going to happen in a qualitative sense, but I'm going to show some mathematical justification for the ideas of Le Chatelier soon enough. So Le Chatelier's principle says that if a system at if a stress is applied to a system at equilibrium, the system will respond in a way that opposes that stress. In a way that opposes the stress. What do we mean by applying a stress to a system at equilibrium? Let's say that you've got a system at equilibrium, such as, I guess we saw it a couple times in those problems, such as when you react hydrogen and nitrogen to make ammonia, or decompose ammonia to make hydrogen and nitrogen. So suppose that you've got a system at equilibrium here. There's some hydrogen in there, there's some ammonia in there, there's some nitrogen in there. And let's say that their concentrations have stabilized and they're at equilibrium. You don't see any visible change to the system anymore. Actually, I think all three of those gases are going to be clear. So maybe visible isn't the right word, but there is no detectable change in the system anymore. Okay, so you've got this system, and let's say I mess with it. So I let it sit down for however much time it takes to reach equilibrium, and then I do one of three things. Let's say, for example, I go ahead and pump in some new hydrogen. Add new hydrogen. And let's write the reaction for this. So I want it to start with nitrogen and hydrogen. Wait. Okay, let me write it in a different color. So 3 hydrogen, giving 2 NH3. Okay. So let's suppose I add new hydrogen after it was already at equilibrium. What's that going to do? Well, since the stress that I've applied is increasing the concentration of reactants, the system will respond in a way that opposes the stress. How do you oppose an increase in the concentration of reactants? By decreasing the concentration of reactants. So, if I add new hydrogen after it's already at equilibrium, then the equilibrium will shift to the right. I'm going to have to proceed right to use up some of my reactant concentration and lower it back down until I reach equilibrium again. If I do the opposite, if I remove hydrogen, so let's say I cross this out, and now let's say I remove some reactant. And let's remove nitrogen this time. It doesn't matter what the reactant is, as long as you're removing some reactant after equilibrium is reached, then you're applying some sort of stress on the reactant side. So if I remove nitrogen, well, now I'm decreasing the concentration of reactants. And how do I increase the concentration back up? Not back up to the same number, mind you, but just, oppose the stress by shifting equilibrium to the left, by having the reaction go to the left. If you start removing nitrogen, then some ammonia, I just realized I mislabeled that, that's a 3. Some ammonia will decompose to form some new nitrogen and hydrogen. So if I add stuff to one side, then the equilibrium will shift away from the side that I added stuff to. And if I remove stuff from one side, then equilibrium will shift towards the side that had stuff removed from it. I could do the same thing with NH3. If I add or remove NH3, so let's cross this out now. Let's suppose I add some NH3. Add some new NH3 to a system that's already at equilibrium. Then I've increased the concentration of products, and to oppose that I have to decrease the concentration of products, so the equilibrium will go to the left to get rid of some of that excess NH3 that I've just added. And if I remove NH3, then of course the opposite will happen, because I need to make up for what's lost. So that's what Le Chatelier's principle is, but it doesn't really explain why things work the way they do. Why is it that the equilibrium shifts right when you either increase reactants or decrease products? Why does it shift left when you decrease reactants or increase products? Well, the reason is because when you add or remove stuff, you're changing the reaction quotient such that it's no longer equal to the equilibrium constant. So before you add stuff or remove stuff, Q is equal to K. But after you add or remove stuff, then, well, Q won't be equal to K. Let's take the example of adding NH3. So the reaction quotient expression for this is going to be Q equals NH3 concentration squared divided by N2 times H2 cubed. Okay, so at some point it's equal to K. What happens if I just add NH3? Well, then I'm increasing the numerator. So now Q is greater than K, and we already know what happens when Q is greater than K. You're not at equilibrium anymore. You're past equilibrium. You're too far right, so you have to go left. So there is a mathematical reason for why Le Chatelier's principle works the way it does. Most chemistry instructors don't go over that because chemists are not mathematicians. If you learn nothing else from me throughout this course, you will learn that chemists are not mathematicians. And again, that's not to say they can't do math, it's to say they don't care enough about the math to explain it to their students. I, however, will not shy away from the math, unless, it's unreasonably hard. I will show the math. So that's one kind of stress you can apply to a system at equilibrium. You can modify concentrations. You can also modify pressures, and you can imagine that would have the same effect, but not always. So modifying the pressure of the container is usually accomplished by letting the container expand, giving it more volume, or by shrinking the container, compressing it, and decreasing the volume. If you remember Boyle's law, pressure and volume are inversely proportional. P1 V1 equals P2 V2. That's Boyle's law. So if I shrink the container, I decrease the volume, that would increase the pressure of all gases in there. And if I increase the volume, then that lowers the pressure of all the gases inside. But even though the increasing or decreasing of pressure is going to have an equal effect on all of the individual gases, depending on the total moles of gas in the container, you could still have a change in the value of Q. You could still have a change in the value of both QP and QC, whether it's based on concentration or pressure. So if, say, I cut the volume in half, which doubles all the pressures, that's also going to double all the concentrations. Okay, so if I double all the concentrations, doubling NH3 concentration means that the numerator would increase by a factor of 4. It's double squared. 2 squared is 4. So doubling pressure, if I cut the volume in half and I double the total pressure in the container, double pressure is going to give me 4 times the numerator, so 4 times NH3 squared, over, what about the denominator? So I'm going to double the N2 concentration and pressure, and I'm going to 8-tuple my hydrogen pressure and concentration. 2 times the hydrogen, if you cube it, 2 cubed is 8, so that's times 8 times the original concentration of H2. After doubling the pressure, this concentration squared becomes 4 times the original. Oh, and I forgot the cube there. This concentration is twice the original, and this concentration cubed is 8 times the original. So overall, the Q has changed by, let's see, 4 over 2 times 8. 4 over 16 is 1/4. So we conclude that this new Q, let's call it Q new, equals 1/4 of Q previous. And Q previous was equal to the equilibrium constant, was equal to K. So if your new reaction quotient is 1/4 of the equilibrium constant, that means it's smaller than the equilibrium constant. That means that you have too few products, too many reactants. Q less than K, you would have to shift to the right. If you increase the pressure on this container, you would have to shift to the right. Increasing pressure would shift equilibrium towards the side that has less moles of gas. So if you increase pressure, you shift towards the side with less moles of gas. If you decrease the pressure, you shift towards the side with more moles of gas. As for a quicker, more intuitive way of predicting what will happen, think of it this way. If I increase the pressure, it's like I'm squeezing the gases together. And if I'm squeezing the gases together, then that means I'm basically trying to force the molecules to collide more often until I get fewer collisions by getting fewer molecules. Squeezing together nitrogen and hydrogen, squeezing together 4 moles of gas into 2 moles of gas, that's something that's kind of intuitive and easy to remember, even if you can't really explain why it happens. That's just an easy way to remember what would happen. And of course, applying the opposite reasoning, if you expand the volume, you lower the pressure, then it's like unsqueezing the NH3, letting it have the freedom to expand and splinter off into more gas molecules rather than less. So increasing or decreasing pressure can shift the equilibrium. How is it opposing the stress? Because if you increase the pressure, the formation of new NH3 by combining your nitrogen and hydrogen, the formation of new ammonia reduces the total moles of gas, which helps reduce the pressure back down. So an increase in pressure is countered by reducing the moles, because reducing the moles of gas helps reduce the pressure back down. You won't get it back down to what it originally was, but you'll have some resistance to this increase in pressure. And similar logic applies for going in the opposite direction. So that's how you're opposing the stress. There is an exception, however. Changing the pressure, whether increasing or decreasing, will have absolutely no effect if the moles of gas on the right equals the moles of gas on the left. If delta N is equal to 0, nothing will change. Equilibrium will not shift at all if the moles of gas on the left and right are equal. So if I had, like my original example, N2 plus O2 giving 2NO, there's not going to be an effect here if you increase or decrease the pressure, because if you do, well, Q is equal to, in this case, NO squared over N2 times O2. If I, for example, double the pressure, then double the nitrogen monoxide squared, that's going to be multiplying by a factor of 4, and double the nitrogen, that's a factor of 2, and double the oxygen, that's a factor of 2. A factor of 4 over 2 factors of 2, that just cancels out. So no effect if you increase or decrease the pressure for a system in which the moles of gas on the left equal the moles of gas on the right. Changing the pressure will have no effect. So only going to work if you have unequal moles of gas on the right and left as determined by the balancing coefficients. Okay, so that's the second type of stress, changing pressure, which is often accomplished by adjusting the volume. And there's a third type of stress that can be applied to a system, which is changing the temperature. Let me redraw this. Actually, do I need to? Well, yeah, let's do that. You know what? No, I'll redraw it. I'll redraw it. It's worth the effort. At least I think it is. Okay, so suppose you have some of this stuff at equilibrium. Or maybe I should do something different. Nah, I'll just stick with this. So we've got some hydrogen in there, some nitrogen, some ammonia, and they're at equilibrium. And I decide to increase or decrease the temperature. Let's say I raise the temperature. Let's say I light a fire under here. So increase temperature. Which way will the equilibrium shift? Again, gonna have nitrogen and hydrogen as the reactants and ammonia as the product. Okay, which way will equilibrium shift? Well, first of all, I would need to know the enthalpy change for this reaction. The response to a change in temperature is based on whether the reaction is exothermic or endothermic. So let me quickly look up the heat of formation of ammonia. Where could it be? LMN, NH3, gas. Heat of formation is negative. Okay, so this is an exothermic process, it looks like. So delta H for this process is negative. I should just say less than 0. It is an exothermic process. Okay. If you increase the temperature for an exothermic process, then you are going to get equilibrium to shift to the left. If you increase the temperature, equilibrium will shift to the left. And if you decrease temperature for an exothermic reaction, then equilibrium will shift to the right. As for the Le Chatelier's principle intuitive explanation for it, you're trying to resist the stress. Increasing the temperature essentially means adding heat. So you want to go in the direction that opposes that. You want to go in the direction that gets rid of heat. If you went to the right when adding heat, you'd be generating more heat for an exothermic reaction. So you don't want to go there. You want to go in the direction that decreases heat. If you're getting extra heat, you're going to want to try and use some of it up. So that's the intuition behind it. If it's an endothermic process, then these are just reversed. If it's an endothermic process and you raise the temperature, it'll shift right. And if it's endothermic and you lower the temperature, it will shift left. But that's just the intuition behind it. What about the mathematical justification for it? What's going on mathematically? So with altering the concentrations and pressures, we saw that this had an effect on Q. It changed Q such that it was no longer equal to K, and it had to go either to the right or to the left to go back to being equal to K. This time Q doesn't change. The temperature doesn't affect Q. It does affect K. If you raise or lower the temperature, you don't change Q, but you do change K. Changing temperature changes K. So Q hasn't changed, it's just that there's a new finish line that it has to chase. Changing temperature changes K. So if the reaction is endothermic versus exothermic, you're going to have different effects. Endothermic versus exothermic. What happens when you increase temperature versus decrease temperature? So increasing the temperature of an endothermic reaction increases K. Increases K. While increasing the temperature for an exothermic reaction will decrease K, and the reverse is true for decreasing the temperature. Decreasing the temperature for an endothermic reaction decreases K, and decreasing temperature for an exothermic reaction will increase K. Increases the equilibrium constant. Why and how? You don't really need to know this, but as I always say, chemists are not mathematicians. Well, I guess I haven't been saying that for quite a few videos now. But if we go back to what I had earlier with the energy diagrams, there it is. remember, increasing temperature increases the rate of both the forward and reverse reactions, but one of them benefits more from the temperature increase than the other. And we saw that the endothermic reaction is more affected by increases and decreases in temperature. The endothermic reaction, because it has a higher activation energy, the effect on the exponent of doubling the temperature, for example, or cutting it in half, in terms of absolute amounts, not in terms of relative amounts, but in terms of absolutes, the absolute value, the magnitude of the exponent, changes more dramatically for the endothermic process as opposed to the exothermic process. So if you increase the temperature, then the endothermic process, the direction that consumes heat, is going to speed up more. And if you decrease the temperature, it's going to slow down more. So then, if we think about it here, increasing temperature, it's going to increase the rate of the endothermic process, whether it's the forward process or the reverse process. That will be increased more. So if you've written it such that the endothermic process is to the right, then the rightward reaction would increase its rate more than the leftward reaction, and equilibrium would lie more to the right. On the other hand, if it's exothermic, then the endothermic process is the reverse process, and so the reverse process would have a greater increase in its rate constant, so the equilibrium position is going to be further to the left. If that all sounds a bit too confusing, then maybe give it some time to just sit there in your head and crystallize a bit. Maybe crystallize isn't the right word, but maybe if you sleep on it, you'll wake up the next day and it'll make more sense. But if it still doesn't make sense by then, you don't really need to know it. It's just for the students that really are curious about the math. It's not something crucial for your course. It's not going to be on your exam in any way. But I think that deeper understanding will help in the long run, especially if you're considering a professional career in chemistry or a related field. Chemists are not mathematicians, but the best chemists are. Okay, so that was Le Chatelier's principle. And yeah, I guess the other thing we can say is that Le Chatelier's principle teaches us how to control reactions that establish an equilibrium. If I can shift equilibrium to the right or to the left by altering pressure, temperature, or concentration, then I have some level of control over how many products and reactants I get. If this equilibrium tends to favor reactants, but I want a lot of products, then all I have to do is every time it reaches equilibrium, pump in more nitrogen and hydrogen, or remove ammonia, and that'll help the reaction continue going forward. And then I can make as much ammonia as I want. Very, very useful if you're a manufacturer who sells ammonia, among other things. So that's the power of Le Chatelier's principle. And I guess the power of equilibrium reactions in general is that you do have some control over them. You can control how much product or reactant you get by doing simple things like altering temperature, concentration, or pressure. All right, let's have a look at some problems now that we have our newfound understanding of Le Chatelier. We're getting to the math-heavy problems. That'll be after this next set. So, 31. The following equation represents a reversible decomposition. Under what conditions. Under what conditions will decomposition in a closed container proceed to completion so that no calcium carbonate remains? Okay, so this is what I was just talking about. So calcium carbonate decomposes, gives you calcium oxide and carbon dioxide gas. The solids have no effect, so it doesn't matter if you increase or decrease their concentrations at all. But the gas is going to have an effect on your equilibrium constants. So what you can do is keep on removing the carbon dioxide. If every time equilibrium is established, you remove carbon dioxide from the system, then more calcium carbonate will have to decompose in order to restore the equilibrium. And it'll keep on happening, and you'll keep on removing carbon dioxide until eventually all of the calcium carbonate is gone. So yes, you can force a reaction towards completion if you continually remove product. 32. Explain how to recognize the conditions under which changes in volume will affect gas phase systems at equilibrium. We already talked about it. As long as delta N is not 0, changing the volume, and thereby changing the pressure, will have an effect, and it will cause the equilibrium to shift. You will change the value of Q, and you'll have to go either forward or backward to get Q back to K. 33. What property of a reaction can we use to predict the effect of a change in temperature on the value of an equilibrium constant? The enthalpy change, whether it's exothermic or endothermic. All right, let's take a look at another set. Uh, 34. The following reaction occurs when a burner on a gas stove is lit. Oh, okay, and it's asking, is an equilibrium among methane, oxygen, carbon dioxide, and water vapor established under these conditions? Explain your answer. So, it's a burner on a gas stove. That's an open system. That's an open system, so every time you make carbon dioxide and water vapor above the gas stove, those gases are just going to leave. They're gonna go out the kitchen window. So you're removing product, which means that the reaction will just keep on going to the right in pursuit of equilibrium, and it'll never get there because you're removing the product as soon as it's made. It's just going out the window. So, no, you're not really going to get an equilibrium here. It's just going to keep on going to the right until you run out of methane or you run out of oxygen. Chances are you're going to run out of the methane first because methane isn't really cheap. Oxygen is free, so it doesn't even matter if methane is cheap. It's still not cheaper than free. One of these days, corporations will also make us pay for the oxygen we breathe. Maybe. Hopefully not, but you never know. There are people in the world that are evil enough to try. 35. Okay, is it similar to 34? Does the equilibrium... No, it doesn't look like it. Okay, I'll give it a read. A necessary step in the manufacture of sulfuric acid is the formation of sulfur trioxide from sulfur dioxide and oxygen, shown below. At high temperatures, the rate of formation is higher, but the equilibrium amount of sulfur trioxide is lower than it would be at a lower temperature. Does the equilibrium constant for the reaction increase, decrease, or remain about the same as the temperature increases? Okay, so the rate goes up. Well, that's always going to be true. If you increase the temperature, the rate always goes up. But it's not about rate. It's about the equilibrium constant. That's what's going to determine how much product you get versus reactant remaining. So if you're getting lower equilibrium amounts of sulfur trioxide, then increasing the temperature must have lowered the equilibrium constant. Lowered it such that by the end of the reaction, you have less sulfur trioxide in comparison with sulfur dioxide and oxygen. And part B, is the reaction endothermic or exothermic? If increasing the temperature lowers the equilibrium constant, in other words, shifts the reaction to the left, then that means it's an exothermic reaction. That would mean it's an exothermic reaction. Number 36. Suggest 4 ways in which the concentration of hydrazine could be increased in an equilibrium described by the following equation. And we see it's an endothermic process. Delta H is positive 95 kilojoules. Okay, so we want to increase hydrazine, which is the product. So we want things that will shift the equilibrium to the right. Okay, I can increase the nitrogen concentration or the hydrogen concentration. Those would both shift equilibrium to the right. I can decrease the hydrazine concentration. That would shift the equilibrium to the right. I can, let's see, are the moles of gas different? Yes, we've got 3 on the left and 1 on the right. So if there's less gas on the right, less gas is favored by higher pressure, so I can decrease the volume of the container, thereby increasing the pressure. That would shift equilibrium to the right. And since it's endothermic, increasing the temperature would increase the equilibrium constant, thereby shifting it more towards products than reactants. So increasing the temperature also increases the production of hydrazine. I think that was more than 4, but there you go. 37, suggest 4 ways. Okay, we already did something like that. 38, how will an increase in temperature affect each of the following? And then how will a decrease in the volume affect them? Okay, so again, increasing temperature will shift equilibrium towards products if you have an endothermic process, and it will shift you towards reactants if it's an exothermic process. As for decreasing the volume, that's the same as increasing the pressure, which will shift you towards less moles of gas. So for the first reaction, we've got 2 moles of gas versus 4 moles of gas. We would shift to the left under increasing pressure conditions. Reaction B, no effect from changing pressure because you've got 2 moles of gas on each side. Part C, we've got 2 ozone, 3 oxygen, so there's less gas on the left, so decreasing the volume would force you to the left. Calcium oxide plus carbon dioxide. Okay, we've got gas on the left and no gas on the right, so increasing the pressure by decreasing the volume shifts you towards less gas, would shift reaction D to the right. If you practice enough, you'll be able to figure out quickly how each of those stresses affect the equilibrium. It can be a little hard to follow when it's your first time, but practice does make perfect. 39. How will an increase in temperature... Okay, so we already did something like this. 40. Methanol can be prepared from carbon monoxide and hydrogen at high temperature and pressure in the presence of a suitable catalyst. Okay, write the expression for the equilibrium constant. We already know how to do that. What will happen to the concentrations if more hydrogen is... Oh, okay, let's talk about this a little bit because we're not just saying which way the equilibrium will shift. This is a little bit more detailed. Let's talk about it. So I'll skip part A. Part B, what will happen to the concentrations of all of those substances if more hydrogen is added. Adding more hydrogen will shift the equilibrium to the right, and if the equilibrium shifts to the right, then that's going to decrease the hydrogen concentration, decrease the carbon monoxide concentration, and increase the methanol concentration. CH3OH is methanol. Now, the hydrogen concentration will decrease because the equilibrium shifts to the right. But overall, you're still going to have more hydrogen than you did before you pumped new hydrogen into the system. If you add new hydrogen, some of it will disappear because the reaction shifts right, but not all of it. You almost never get rid of all of the new stuff that you put into a reaction at equilibrium. So it will decrease, but still be more than it was before you added the hydrogen in the first place. Part C, what will happen to the concentrations if carbon monoxide is removed? Did I call it carbon dioxide earlier? I might have. If I did, I meant to say carbon monoxide. So if we remove carbon monoxide, decreasing concentration of reactants, that would mean that the reaction has to proceed left in order to restore equilibrium. So in that case, the concentration of hydrogen would go up, the concentration of carbon monoxide would increase, but it wouldn't increase all the way back to what it used to be, and the concentration of methanol would decrease. Part D, what will happen if methanol is added? That would increase concentration of products, so you'd have to shift to the left. So you would increase the concentration of hydrogen, increase the concentration of carbon monoxide, and decrease the concentration of methanol, but you'd still have more methanol overall than before you added some new methanol. You'd still have more overall, even though it does decrease just after adding. So maybe you add, I guess I want to make this a bit more concrete. So let's suppose we added 2 extra molars. Let's say you started with 5 molars of methanol, and that's what it was at equilibrium, and then you added 2 molars of new methanol, so now you're at 7. You're going to lose some of that, but you're not going to go down to less than 5. You'll still be above 5 at the end, so you might be at like 5.5 molar of methanol after adding 2 molar to what used to be 5. Putting some concrete numbers on it can sometimes make it easier to grasp. But yeah, that's the essential idea. Part E, what will happen to the concentrations if the temperature of the system is increased? Delta H is negative. This is an exothermic reaction, and so you can think of the heat as being on the right side of the equation. You can think of the heat as being a product, and increasing temperature is basically increasing heat. Increasing product means shift towards reactants. So you would shift left. So that means you would increase hydrogen concentration, increase carbon monoxide, and decrease methanol. Part F, what will happen to the concentrations of hydrogen, carbon monoxide, and methanol at equilibrium if more catalyst is added? Nothing! Catalysts have no effect. They just affect how quickly you get to equilibrium. They do not affect where the equilibrium is. Never, ever, ever. Okay, let's move on to the next sheet. 41 similar to the one we just did, 42 similar to the one we just did, so you can practice those on your own. Next sheet. Pure iron metal can be produced by... Okay, more of the same, so we'll skip that. 44. Ammonia is a weak base that reacts with water according to this equation. Will any of the following increase the percent of ammonia that is converted to the ammonium ion in water? So will any of these shift the equilibrium to the right, in other words? Adding sodium hydroxide, that would increase the hydroxide concentration. Hydroxide is a product. If you increase it, equilibrium shifts to the left, so that's a no. Adding hydrochloric acid, that would work, but it's hard to see why until you learn more about acids and bases. If you add hydrochloric acid, then that's going to neutralize the hydroxide ions. So adding acid will neutralize hydroxide. It'll remove it from the equation because it'll just turn the hydroxide into ordinary water. So adding HCl really means removing OH minus. And removing OH minus, removing product, will shift the reaction to the right. And then part C, addition of ammonium chloride. So ammonium chloride is going to easily dissociate into NH4 plus and Cl minus. Cl minus is not going to affect the equilibrium of the reaction that they have for this problem because chloride isn't really in there. It's a spectator ion. But the ammonium ion, the NH4 plus, will have an effect. If you're adding NH4 plus in the form of NH4Cl, then you're increasing the stuff on the product side of your equilibrium, so equilibrium will shift left, so that's a no. The only one that will increase the conversion of ammonia to ammonium is B, addition of hydrochloric acid. Number 9. So, well, I'm saying number 9. Actually, it's probably not even the 9th slide. I probably lost count. But anyway, slide 9-ish, maybe it's like the 10th or 11th by now. Acetic acid is a... Okay, so same as the previous problem, same ideas. We'll learn more about dealing with weak acids in the next chapter, so don't worry too much about problems 44 and 45. We'll see more of that in the next video. 46 suggests 2 ways in which the equilibrium concentration of silver ion can be reduced in a solution of sodium ion, chloride ion, silver ion, and nitrate ion in contact with solid silver chloride. Okay, if you want to decrease the concentration of Ag+, and you have it on the left side of the reaction, you want to shift your reaction to the right. So anything that shifts your reaction to the right will do the trick. We've seen examples like this before, so I'm not going to go over that. You know the ideas by now. 47, how can the pressure of water vapor be increased in the following equilibrium? Oh, equilibrium between a liquid and its vapor, vapor pressure. Vapor pressure always increases when you increase the temperature, because the evaporation of any liquid is always going to be an endothermic process. Increasing the temperature for an endothermic process increases the equilibrium constant, shifts you towards the product side. So yeah, That one is pretty straightforward. Even without knowing equilibrium, you should have known how to answer that just from understanding the idea of vapor pressure, which we've covered numerous times. 48, a solution is saturated with silver sulfate and contains excess solid silver sulfate. Okay, a small amount of solid silver sulfate containing a radioactive isotope of silver is added to this solution. Within a few minutes, a portion of the solution phase is sampled and tests positive for the radioactive silver ions. Explain this observation. Ah, really interesting question, and this gets to the heart of dynamic equilibrium as opposed to static equilibrium. So the solution's already saturated. So the maximum amount of silver ions and sulfate ions are already in there. And if you add more solid silver sulfate, but some of the silver in that solid is radioactive, it's not that none of it dissolves, it's that an equal amount dissolves as you have precipitating. So some of the silver ions and sulfate ions that are already in the saturated solution will go back to being solid, while some of the new solid silver sulfate turns into ions, and that's why some of those radioactive silver ions can dissolve into the solution even though it's already saturated, as long as you exchange it with an equal amount of non-radioactive silver ions precipitating. So yeah, that just gets to the heart of the fact that it's not static equilibrium, it's dynamic equilibrium. Stuff is still changing, it's just that on a macroscopic scale, you can consider things being stable. 49, the amino acid alanine has two isomers, alpha alanine and beta alanine. When equal masses of these two compounds are dissolved in equal amounts of a solvent, the solution of alpha alanine freezes at the lowest temperature. Which form, alpha alanine or beta alanine, has the larger equilibrium constant for ionization? And then they've got the equation there, so HX, since alanine is an amino acid, it's an acid, so it's going to be hydrogen attached to some anion, and they're just using X to represent that. So the X represents alanine. So yeah, which one is going to have the larger equilibrium constant? I like this because it calls back to video number 11, colligative properties. Alpha alanine freezes at the lowest temperature. The decrease in freezing temperature is proportional to the molality, which is proportional to the number of moles of ions that you make. Remember your Van Hoff factors? In this case, both forms of alanine have a Van Hoff factor that's between 1 and 2. It's going to be some fraction. And that's because an equilibrium is reached. Alanine doesn't completely dissociate into hydrogen ions and whatever you call the anion for alanine. So, if we've got alpha alanine has a lower freezing temperature, that means its freezing point depression is higher, which means even though you put in equal amounts, even though they're equal molalities, the Van Hoff factors are different. The one that freezes at a lower temperature must have had a higher Van Hoff factor, which means it dissociated more, which means it went more to the right in that equilibrium that they've shown us, which means it has a higher equilibrium constant. So alpha alanine has the larger equilibrium constant for ionization. Okay, that was a good problem to wrap up with for this section. Let's take a look at some new concepts before we move on to some more problems. Okay, so now we're going to get into the math-heavy stuff. So let me pull up. I should have prepared this ahead of time, but let me just dig it up in my book real quick. I know I have something in here that I can use as an example for what I'm about to cover. The mathematics of equilibrium constants. So you might remember a while back, I think in video number 6, we introduced an idea called Hess's law, and we kind of reviewed it in the previous video as well. We reviewed something similar, which was reaction mechanisms. What both of those have in common is that you can combine a number of step reactions and get an overall reaction. And when doing Hess's law specifically, what we did was we took a bunch of known reactions and we knew their enthalpies, and we wanted to calculate the enthalpy of the overall reaction based on the enthalpy of the individual steps. Well, you can do something similar with equilibrium constants, but the rules are a bit different. So let's have a look. I've got the following set of equations, which I think I might have actually used as an example in the thermochemistry video. So hydrogen plus fluorine forming 2-hydrofluoric acid, and carbon, I guess I should label the phases here, gas, gas, gas. Carbon is solid plus 2-fluorine gas gives us CF4 gas. And then, let's see, we've got 2 solid carbon plus 2 hydrogen gas gives us C2H4 gas. All right, and the overall reaction that we're looking at is C2H4 gas plus 6F2 gas forming or in equilibrium with 2CF4 gas plus 4HF gas. Okay. So I'm not going to put actual numbers to this, but let's just say that the equilibrium constants for each of these steps are K1, K2, and K3. And let's say they're all based on concentration and not pressure. And I want to figure out what's the equilibrium constant of this overall reaction. Is there a way to do that by combining the equilibrium constants of these 3 steps? First, I'm going to need to order the steps in order to get the correct overall reaction. So let's do that. Actually, before I do that, let's write the expressions for K1, K2, and K3. So K1 is going to be HF squared over H2 times F2. K2 is going to be CF4 over, well, carbon doesn't count, so just over F2 squared. And over here, carbon doesn't count, so it's just going to be C2H4 over H2 squared. Alright, so what we're trying to get, we're trying to determine K overall, which is going to be CF4 to the second power times HF to the fourth power divided by, it looks like C2H4 to the first and fluorine gas to the sixth. Okay, let's figure this out, piece it together piece by piece. So, if I have C2H4 on the left here, then I need to have a C2H4 on the left for at least one of these. This is the only one that has C2H4 in it, so this has to be on the left. This has to be flipped. So I'm going to have to flip that equation. And if I flip it, maybe I should do it on a separate sheet so that we don't lose track of things. So if I flip it, then I get C2H4 gas, not plus, in equilibrium with 2 hydrogen and 2 carbon. 2 carbon solid and 2 hydrogen gas. Okay, so now that I've flipped this equation, what happens to its equilibrium constant? When we were dealing with enthalpies before, what I would do is I would just take the negative of the delta H anytime I flipped the reaction. So if delta H for this reaction was, say, 35 kilojoules and I flipped it, then delta H for the new equation would be negative 35 kilojoules. What about for equilibrium constants? Do I make it negative? Well, negative equilibrium constants don't make sense. Here's what happens instead. Just without knowing anything about these original equilibrium constants, what would you do if I asked you to write the equilibrium constant for this? Well, you would do products over reactants, so let's do that. Let's do that. K equals products H2 squared, don't count the carbon since it's solid, over C2H4 to the first power. Okay, so that's the equilibrium constant for this flipped reaction, but wait a minute. What do these two have in common? They're reciprocals of each other. So this new K is actually equal to the reciprocal of K3. You can either write it as K3 to the negative 1 or 1 over K3, which is what I'm going to prefer writing. Okay, so K for this new flipped reaction is 1 over the K of the previous reaction. If you flip a chemical equation, then you also flip the equilibrium constant. You take the reciprocal, not the negative this time. It's not the same as what we did with enthalpy. Okay, so there's that. So I flipped that, and I'm going to need to have one C2H4 there, so definitely not going to multiply this. Just going to leave it there. What else? I need to have CF4 on the right, so that's fine. I have CF4 on the right there, but I need 2 CF4, so I'm going to need to multiply that. I need to have HF on the right, and it looks like I don't need to flip this either, but I do need to multiply it by 2. Okay, so I need to multiply both of those by 2. Let's go ahead and do that. Let's go ahead and do that, and let's see what that gets us. So I'm going to multiply that first one by 2, and that's going to be 2H2 plus 2F2 gives us 4HF. And I should probably mention that they're all gases. Okay, how would I normally write the equilibrium constant for this? I would say K equals HF to the 4th over H2 squared times F2 squared. But wait a minute. How does that compare with K1? That's equal to all of K1 squared. This is equal to, if I take HF squared over H2 to times F2, and I square all of that, then it becomes HF to the 2 times 2, which is 4, H2 to the 1 times 2, which is 2, and F2 to the 1 times 2, which is 2. Ah, so this is equal to K1 squared. So that's equal to K1 squared. The new equilibrium constant after you multiply an equation, whatever you multiply by becomes the exponent of the original K to give you the new K. So multiplying by 2, you square. Multiplying by 3, you take K1 cubed. If I multiplied by 5, I would take K1 to the 5th. If I divided by 2, I would take K1 to the 1/2, which is the same as the square root of K1, and so on and so forth. Okay, so for that, multiplying by 2 squares the K, and I'm multiplying this by 2 as well, so that's going to square the K as well. Let's go ahead and do that in a different color. I guess I'll do magenta, and I guess I'll do it down here. So we've got 2 carbon, 4 fluorine, 2 solid carbon plus 4 fluorine gas in equilibrium with, that's going to be 2 carbon tetrafluoride. 2 carbon tetrafluoride. Okay, and so the K for this thing is going to be, of course, CF4 squared over carbon doesn't count over F2 to the 4th. So CF4 squared over F2 to the 4th, which equals the square of, I'm not going to be able to fit that in there, which equals the square of CF4 over F2 squared, which equals K2 to the 2nd power, equals K2 squared. Okay, so we've seen the effect on the equilibrium constant of flipping an equation. We've seen the effect of multiplying, and therefore dividing, because division is really just multiplication by a fraction. What about adding equations to each other? What about when we combine them? We can now combine these three flipped equations. We can cancel out the carbon, which shows up on both sides. We've got 2 carbon solid there, cancels out there. We've got 2 hydrogen gas here, cancels with 2 there. And we're left with 6 fluorine gas, a C2H4, 4 hydrofluoric acid, and 2 carbon tetrafluoride. So we're left with the overall reaction that was requested of us originally. C2H4 plus 6F2 gives 2CF4 plus 4HF. So how does the equilibrium constant for this relate to 1 over K3, K1 squared, and K2 squared? Well, it turns out that if you multiply them, you'll actually get this K overall. So when you combine equations, you just multiply their equilibrium constants. K overall is going to be equal to K of this step, which was 1 over K3, times K of this step, which was K1 squared, times K of this magenta/pink step, which was K2 squared. If I add reactions together, their equilibrium constants multiply, and maybe you don't believe me, so we're going to go ahead and work this all out. Where do I want to do it? I guess I'll do it here. We've got some big empty space here, so let's make use of this. Okay, 1 over K3, that's H2 squared over C2H4 times K1 squared, which is HF to the 4th over H2 squared times F2 squared, and then times K2 squared, which was CF4 squared over F2 to the 4th. You'll notice that the hydrogen concentration is going to cancel out, and it canceled out when we were combining the equations too. If it showed up on the product side and then on the reactant side, or vice versa, in the same amounts, then in one of your steps it's going to show up in the numerator, and in a different step it's going to show up in the denominator. So not only does it cancel out in the chemical equations, it also cancels out in multiplying the equilibrium constants. You had 2 moles of product H2 and 2 moles of reactant H2, so one of them is in the numerator, one's in the denominator. They're gone. They cancel out. Okay, and fluorine, we had 2 on the reactant side and then 4 more on the reactant side, so we got a fluorine squared and a fluorine to the 4th, both in the denominator, combined to become fluorine to the 6th. So I think with that you can see why multiplication works. Multiplication pits the numerators against the denominators. And if you have things that show up in the numerator of one equilibrium constant and the denominator of another, you get them to cancel out. So it makes sense that multiplication would work here. Was there anything else that canceled out? I don't think so. Yeah, nothing else. Okay, so it's going to be HF to the 4th times CF4 squared over C2H4 times f2 to the 6th, which is exactly equal to our overall k value as I defined over here. Let's see, can I show those on the screen at the same time? Yeah, so I wrote these in different orders: CF4 squared, CF4 squared, HF to the 4th, HF to the 4th, F2 to the 6th, F2 to the 6th, C2H4, C2H4. So there you go. Remember this for the next video. We're not going to do any more of these for the remainder of this video, but remember these ideas. Remember these ideas for the next video, because we're going to use it to justify something that we'll be using quite a lot. When you flip reactions, you take the reciprocals of their equilibrium constants. When you multiply reactions, you exponentiate their equilibrium constants. And when you add, in other words, combine reactions, you multiply their equilibrium constants. Remember those 3 rules. All right. Now then, for the rest of this video, we're just going to be looking at calculations involving equilibrium constants. So, here's a problem that we still haven't dealt with, and I'm sure some of you have been wondering about it. I think we saw at some point, I forget which problem it was, but I think I remember we saw something with an equilibrium constant of 17. Maybe I should go back and look up that problem. Let's hide that. And let's see, where is my... I know it caught my eye earlier. Ah, there it is. Okay, I found it. So I'll just put it in front of you. Part A of problem 17, we saw that the equilibrium constant, I was about to say concentration, the equilibrium constant is 17, and I mentioned that this wasn't at equilibrium and that we could calculate how much of the nitrogen, hydrogen, and ammonia you would have to have by the time equilibrium is reached. So let's go ahead and address that sort of problem. I'm going to do something a little bit different. I'm just going to assign new initial concentrations, but still keep with the same idea. So we've got, at some temperature, they didn't tell us, Kc is equal to 17 for the following reaction: decomposition of ammonia into 3 moles of hydrogen gas and 1 mole of nitrogen gas for every 2 moles of ammonia. And I'm not going to label them as gases because I think we've seen these enough times to know that they would be gases at room temperature. That's assuming this is even happening at room temperature at all. And let's say that I started this reaction with, let's say we started with an initial concentration of ammonia, NH3 initial equals, let's do 2.00 molar. And the initial concentrations of these guys will just be 0. So I put some ammonia into an otherwise empty flask or container, and I just let it go. I seal the container and I let it do its thing. So concentration of hydrogen, initial will be 0, and initial concentration of nitrogen will be 0. I'm wondering if I'm going to run into an algebraically messy problem here. Maybe I shouldn't have used this as the first example. But we'll see how this goes. If it turns out to be too difficult to solve algebraically, then we'll just abandon ship and try something different. So when dealing with this sort of problem where the question they're asking is typically going to be, what are the equilibrium concentrations? In other words, what are the final concentrations? What are the equilibrium and or final concentrations? Equilibrium concentrations means concentrations at equilibrium, means final concentrations. I know to some of you that might be obvious, but you'd be surprised how many students don't understand that equilibrium concentration means final concentration. So, for dealing with this type of problem, teachers will typically tell you to put together an ICE table, and some people also call it a RICE table. I typically just go with the ICE table. I don't see the point of putting the reaction in the table, but you know, I'm going to include it because some teachers do, and I don't want to cause too much confusion. So, R stands for the reaction. You write the reaction in here, or rather the substances in the reaction. So, ammonia, hydrogen, well, okay, I'll just write the reaction itself. The hydrogen and the nitrogen. Okay. Then, in the I row, I stands for initial. This is where you write down the initial concentrations. So, the way I have it, we've got 2.00 molar is the initial concentration of NH3, and 0 are the initial concentrations of hydrogen and nitrogen. Then, over here in the C column, the C stands for change. What is the change in the concentrations? So first you'd have to predict which way the reaction will proceed. And usually it's going to be pretty easy, but you know how to do it. Calculate the reaction quotient and compare it to the equilibrium constant. Usually you won't have to do that because it'll be super obvious, like in this case. Which way is it going to go? There's only one way it can go. You can't form ammonia out of hydrogen and nitrogen that aren't even there, so the only way you can go is to the right. So in this case, we're going to lose some amount of ammonia. We're going to lose some amount of ammonia. And I'm going to say we're going to lose 2x molar worth of ammonia. Why the 2? Because of the balancing coefficients. So for every 2x molar of ammonia that I lose, I'm going to gain 3x amount of hydrogen and gain 1x molar of nitrogen. So for example, if, and this is just hypothetical, if x was 0.1 molar, for example, then for every 0.2 molar of ammonia lost, I would gain 0.3 molar of hydrogen and 0.1 molar of nitrogen. It's just based off of the balancing coefficients. For every 2 you lose here, you gain 3 here and 1 here. So for every 2x you lose here, you gain 3x here and x here. I could have just called this x, and then this would be 3/2 x, and then this would be 1/2 x, but do you really want to deal with those fractions? I didn't think so. Okay, and then E stands for equilibrium. So reaction, initial, change, and equilibrium. What is the equilibrium concentration, or final concentration? Well, after you lose 2x, the concentration of ammonia will be 2 minus 2x. And for hydrogen, you're going to have 0 plus 3x is just 3x, and 0 plus x is just x. All right, so those are the equilibrium concentrations. We don't know what they are yet, that's why we're using x's, but we might be able to calculate them because we know something about the equilibrium concentrations. We can use their ratios to get the equilibrium constant. If this reaction reaches equilibrium, then the equilibrium constants will be such that they equal Kc. They equal 17 if I take products over reactants. So if I take the hydrogen equilibrium concentration cubed, that is 3x cubed, times the nitrogen's equilibrium concentration to the 1, that is x, divided by the ammonia equilibrium concentration squared, so that's 2 minus 2x squared, then that should be equal to 17. And I think this one's actually going to be solvable. Oh, we might actually have to do a quadratic formula here. That happens sometimes with these, so yeah. I hope you're a fan of the quadratic formula. Yay! It's not bad, it's just time-consuming and tedious. Okay, so let's simplify this a bit. 3x, if I cube it, that becomes 27x cubed. The 27 is an exact number. So we've got 17 is equal to 27x cubed times x is 27x to the 4th over, you might be tempted to FOIL this. I'm not going to do that, at least not yet. I'm just going to keep it written as 2 minus 2x quantity squared. Okay, so a lot of students will try and FOIL this out and it'll get really messy really quickly. Don't do that, since you've got even exponents in the numerator and denominator. The first thing you can do is square root. Actually, before that, I'm going to divide by 27. So I'm going to do 17 over 27. 17 over 27 equals x to the 4th over 2.00 minus 2x quantity squared. And then if I square root both sides, if I square root both sides, then whatever the square root of 17 over 27 is, that should have, well, 17 is 2 sig figs and 27 is exact, so 2 sig figs. Square root of 17 over 27 is about 0.79, so I've got 0.79 equals, the square root of x to the 4th is x squared over the square root of 2 minus 2x squared is just 2 minus 2x. And there we go. Now, multiply 2 minus 2x over to the left-hand side, and let's solve for x. Let's start that on another sheet. So I'm going to copy down my numbers. Let's see. So I'm going to do 0.79 times this stuff. So 0.79 times 2.00 minus 2x equals, well, x squared. Okay, let's distribute the 0.79. So 0.79 times 2.00 is 1.58, which I'd have to round to 1.6 because 2 sig figs times 3 sig figs. So we've got 1.6 minus, that's an exact 2, so 2 times 0.79 Oh, well, it's still going to round to 1.6 anyway because that has 2 sig figs. Equals x squared. We need to get this in the form of a quadratic equation. So one of the sides of the equation has to be 0. I'm just going to move this stuff over to the right. So we get 0 is equal to x squared. Add 1.6x over to the right. And subtract 1.6. And now good old quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. We've got 2 possible values for x. Only one of them is going to be realistic. Let's go ahead and plug in the numbers. So we've got b is 1.6. So negative b is negative 1.6 plus or minus the square root of 1.6 squared minus 4 times a times c. A is 1, exactly 1, and c is negative 1.6. And then all that over 2a, all that over exactly 2 times exactly 1. And yeah, this is the point where everybody just kind of goes, screw the sig fig rules, and we just, you know, do whatever. So I'm just going to plug all this into the calculator at once, and we'll just have 2 sig figs in the end. That seems to be what we're trending towards. A bit crude, but it's not worth it to nitpick over every little step at this point. So I'm going to do plus the square root and see what that gives me. And then I'm going to do minus the square root and see what that gives me. Okay, so if I do plus the square root, then I'm getting x equals approximately, if I round it to 2 sig figs, that's going to be 0.70. I'm getting 0.70 molar. And the other one that I get is x approximately equals negative 2.3 molar. So there are times when a negative makes sense. A negative answer would make sense if you assumed the reaction went forward when in reality it actually goes backwards. So that would happen if you failed to compare Q against K before deciding whether the reactants increase or decrease and whether the products then increase or decrease. So if you fail to do that, then getting a negative x value might still make sense, but usually it won't, assuming that you knew the correct direction where the reaction would proceed in the first place, which isn't that hard to do, so I would expect you to do that, in which case negative answers would never make sense. Sometimes you do get the direction of the reaction correct, but both of your answers come out positive. So what if this was still 2.3, but it came out positive? It would still be wrong because you can't subtract 2.3 molar when all you had was 2 molar to begin with. So even if both of your answers come out positive, one of them is going to be unrealistic. So no matter what, if you find yourself having to solve a quadratic equation at all, it's guaranteed that one and only one of the 2 solutions is correct. The other one is always going to be unrealistic, either because it's got the wrong sign or because it's got the wrong magnitude, or both. So keep that in mind. So it looks like X is about 0.70 molar. That's what we're going to go with. So what are the final concentrations? What are the equilibrium concentrations? Well, if X is 0.70 molar, then I've got 2.00 minus 2 times 0.70. That's an exact 2, so it's going to be 2.00 minus 2 times 0.70. That's minus 1.40. Or is it 1.4? No, it would be minus 1.4. So 2.00 minus 1.4 is going to be 0.60. 2 sig figs. Wait. No. Because you'd have minus 1.4. Yeah, it would just be 0.6. Okay, 1 sig fig. Because it's not about sig figs. Once you're subtracting, it's decimal places. Okay, so 0.6, and then 3x. 3 times 0.70 is going to be 2.1 molar. And that's just going to be 0.70 molar. Okay, and just to be on the safe side, let's check if this actually works, if this actually gives us 17 or approximately 17. So if I plug those in to my equation for reaction quotients, then I'd have 2.1 cubed times 0.70 to the 1. That's for hydrogen and nitrogen respectively, over ammonia squared, so over 0.6 squared. And I guess I'm gonna ignore the sig fig rules a bit here. But if I plug that stuff into my calculator, 2.1 to the 3rd power times 0.70. Whoops, no, not in the exponent. I hate it when my calculator does that. Divided by 0.6 squared is about 18, so close. Close. It's not going to be exact because, you know, we had to round and stuff. So, yeah, about 18. It checks out, so we did get it. We didn't get it very precisely, but we got it. And yeah. So that's the rest of the video. We're just going to do more problems, most of which, if not all of which, are going to involve these rice tables. And of course, eventually you're going to want to graduate from rice tables. You're going to see some patterns that are common enough where you can sort of see the rice table in your head and you don't actually have to write it out. You can just jump straight from this to this. So yeah, that's something that you're going to want to aspire to. There are some problems where you don't really need to write out the rice or ice table. If you can picture it in your head and it's not as hard to do as it sounds, then you can save yourself a lot of trouble. You can reduce the amount of writing work you have to do. Oh, one more thing before we look at problems. So there's, of course, other types of K that I should probably talk about. Let's do that on a separate sheet. Other types of K. Other types of K. Now, what all K values have in common is that they always have the same formula. Products over reactants raise each product to an exponent equal to its balancing coefficient. raise each reactant to an exponent equal to its balancing coefficient. So same formula, same format, same everything, but sometimes we label them differently depending on the type of reaction that we're dealing with, and that's just for the sake of convenience, to easily communicate what type of reaction specifically we're looking at, because there are different categories of reactions that have useful patterns that we can take advantage of, and being able to signal that is convenient, but it doesn't mean that it has a different formula or anything like that. They're always still going to be of the form K equals final concentrations of products raised to some power n products divided by final concentrations of reactants raised to some number of moles of reactants based on balancing coefficients. So they're always going to have this same format. If all else fails, you can always rely on this. But there are some other types of K that we will be seeing in the next 2 videos. So, of course, there's just the ordinary K. Sometimes it's called KEQ, standing for equilibrium. We've got Kc and Kp, which are just different in terms of whether you use concentration or pressure to calculate them. We have Ka and Kb. We have Ka and Kb. These are for the dissociation of acids and bases. We're going to see a lot of that in the next video. The acid dissociation constant and base dissociation constant is what they're typically called. So these are the equilibrium constants for whenever you put a weak acid or weak base in water. The ionization process, the partial ionization process that happens, because it's a weak electrolyte, so it's not going to completely ionize, but the partial dissociation or ionization process that occurs when you put a weak acid or weak base into water, the equilibrium constant for that is called Ka or Kb, depending on whether it's an acid or a base. But really, it's the same as all the other Ks. Products over reactants. Products over reactants. We're also going to see something called KSP. The SP stands for solution product or solvation product. This is associated with reactions like what we had in an earlier problem, actually, with silver and lead. Let me see. Was it? Yeah. So the equilibrium constant for a reaction like this, since the reactant side is going to be solid, which doesn't contribute towards the equilibrium constant, there's nothing to divide by, or you can divide by 1. So rather than a quotient, this is just a product. You multiply 2 or more things, and there's nothing to divide by. So that's why it's called a solvation product or a solution product. So that's KSP. And I don't know whether or not I'm going to want to talk about it, but there's also something called Kf, which is a formation constant. This is associated with the formation of complex ions. Those are also equilibrium processes, so they're going to have equilibrium constants as well. Again, not sure if I'm going to want to talk about those in the upcoming videos, but we'll probably give them some honorable mention in the final video, number 20, which is all about complex ions and compounds that contain them. So yeah, that's what's coming up. So those are just other types of K, but again, no reason to freak out. Don't feel like you have to memorize different equations for these. They're all the same formula. The subscripts just indicate contexts, specific types of reactions or specific patterns that were worthy of getting their own name, their own brand of K. Okay, so yeah, I guess the rest of this video is just going to be problems, so let's get to it. Let's do a few of these and wrap things up. This is the intro to equilibrium, so I don't want it to overstay its welcome. Where do we start? Okay, let's take a look at these and see if there's anything worth note. A reaction is represented by this equation. A plus 2b gives you 2c. Write the mathematical expression for the equilibrium constant. Using concentrations less than or equal to 1 molar, identify two sets of concentrations that describe a mixture of A, B, and C at equilibrium. Oh, interesting. So we can make up whatever concentrations we want to have this at equilibrium. Okay, let's give that a shot. So we've got, I'll copy down the equation. So it was A plus 2B yields C. All of them are in the aqueous phase. Oh, yields 2C. I don't know if I said the 2 earlier. A plus 2B gives 2C. Okay, so the equilibrium constant in terms of concentration is going to be concentration of C squared over concentration of A times concentration of B squared. And then they told us that the equilibrium constant was 1 times 10 to the 3. And they want us to use concentrations less than or equal to 1 molar and find a set of concentrations where this system would be at equilibrium. Okay, so here's an easy one. I'm going to make C and B equal to, actually they can be anything as long as I make them the same. So let's make them 0.2 molar, for example. I can have C, its final concentration being equal to 0.2 molar, and I can have the final concentration of B equal to 0.2 molar. And if I do that, then it'll be 0.2 squared over 0.2 squared. They'll cancel out. And to get 1 times 10 to the 3, all I would have to do is have the concentration of A be 1 times 10 to the negative 3. Because then 0.2 squared over 0.2 squared is 1, over 1 times 10 to the negative 3 is 1 times 10 to the positive 3. There we go. So that's a cheap, simple combination of concentrations that lets Q equal K. And then they said they wanted a second one. So I guess you could do the same thing, but change these and make them both 0.3, for example. If you want to go the easy route, then that's what you would do. But maybe you don't want to go the easy route. Maybe you want to do something like, how do I make this just a little bit more complex? Not too much. Let's make C twice as large as B. So let's say the final concentration of C is, let's make it 0.8 molar, and have the final concentration of B, whoops, B, not C. Let's have that be 0.4 molar. Okay, in that case, 0.8 squared over 0.4 squared, 0.8 over 0.4 is 2, and then 2 squared is 4. So we've got a 4. We need to divide it by the final concentration of A to get 1 times 10 to the negative 3. So really simple solution. Make the final concentration of A equal to 4 times 10 to the negative 3, and then that'll work out. 0.8 squared over 4 times 10 to the negative 3 times 0.4 squared will give you 1 times 10 to the 3, if my math is right, and I do think my math is right. Okay. What else do we have? 51 is basically the same, it looks like. 52. What is the value of the equilibrium constant at 500 Celsius for the formation of ammonia according to the following equation? An equilibrium mixture at 500 degrees Celsius was found to contain 1.35 molar hydrogen, 1.15 molar nitrogen, and 4.12 times 10 to the negative 1 molar ammonia. Okay, those concentrations they gave us aren't initial concentrations, they are the equilibrium concentrations. So all you have to do is plug them into your reaction quotient expression, and you're already at the place where your reaction quotient is equal to your equilibrium constant. So I'll just set it up. So you're already at equilibrium because those are equilibrium concentrations. You're at the place where Q equals K equals products were 2 moles of ammonia, so NH3 squared, over reactants 1 mole of nitrogen and 3 moles of hydrogen, so H2 cubed. So all you have to do is plug in the values. They said NH3 was 4.12 times 10 to the negative 1. N2 was, what did they say? 1.15, and H2 was 1.35. Plug them in, calculate your K. Easy peasy lemon squeezy. Or however people say it. Okay. Is 53 any different? What is the equilibrium constant for the reaction if a mixture at equilibrium contains gases with the following concentrations? Okay, so 53 is the same as 52. Same idea. 54. A 0.72 mole sample of PCl5 is put into a 1 liter vessel and heated. At equilibrium, the vessel contains 0.40 moles of PCl3 and 0.40 moles of Cl2. Be careful, those are not molarities, those are moles. You have to divide by the volume to get the molarities. But the volume is 1 liter, so dividing by 1 just converts the moles to molars. So I guess even if you didn't notice that they were given in moles, you would have gotten away with it. Calculate the value of the equilibrium constant for the decomposition of PCl5 to PCl3 and Cl2 at this temperature. Again, they told you, oh, well, there is a bit of math to do here. There is a bit of math because they told us the initial concentration of one of them and the final concentrations of 2 of them. Okay, let's work this one out. Always be mindful of what your concentrations mean when looking at these problems. It's very easy to make mistakes if you don't realize when you're dealing with initial versus final concentrations. So we've got 0.72 moles of PCl5. And it decomposes into PCl3 and Cl2. So I guess rice. Okay. And you start off with none of these. So they said it was put into a 1 liter vessel. It's 0.72 moles over 1 liter, so it's 0.72 molar. And in the end, after the vessel is heated and allowed to settle and everything, the vessel contains 0.40 moles of PCl3 and 0.40 moles of Cl2. So at equilibrium, Was it 0.4 for both? Yeah. Oh, well, of course it would be because, yeah, their balancing coefficients are the same. So 0.40 moles over 1 liter is 0.40 molar for each. Wait, did I? Not liters, molars. Okay. And yeah, we just need to fill out the rest of this table and figure out what's the equilibrium concentration of PCl5, because they didn't mention it. Not that it's too hard to do, it's really simple stoichiometry. How much PCl5 did you lose? Well, we know that starting from 0, we must have gained 0.40 molar of each of these. And based on the balancing coefficients, it's all 1 to 1 to 1, so gaining 0.4 of each of these must mean losing 0.4 of your PCl5. And so that tells me that the final concentration, or equilibrium concentration, of PCl5 is 0.32 molar, and there you go. All three of those were gases, right? Well, they don't say that the PCl5 is a gas, but I'm pretty sure it is. Otherwise, this would have been a pointless problem. So yeah, I'm going to assume that PCl5 is also in the gas phase, in which case you can now calculate the equilibrium constant. K equals Q at equilibrium, which is Q final, which is final concentration of PCl3 times final concentration of Cl2. So 0.4 times 0.4 over final concentration of PCl5, which is 0.32. Okay, 0.4 times 0.4 over 0.32. I guess since I went to the trouble of writing it out, I might as well calculate it. Okay, that's 0.50. So that's pretty close to 1. So yeah, your products and reactants are about evenly split. This reaction isn't overwhelmingly in favor of products, nor is it overwhelmingly in favor of reactants. Magnitude of K is pretty close to 1. Okay. That was the last one on that page, so let's pull up our next page and see what we've got here. 55 at 1 atmosphere and 25 Celsius, nitrogen dioxide with an initial concentration of 1 molar is 0.0033% decomposed into nitrogen monoxide and oxygen gas. Calculate the value of the equilibrium constant for the reaction. Okay, so they've given us percent decomposition, and that's something we'll see with acids and bases in the next video. In the case of acids and bases, we'll call it percent dissociation or percent ionization. But yeah, so I'm just gonna go with the setup and just describe the basics of what you need to do. It's really not that hard. If you've got 1 molar of nitrogen dioxide and 0.0033% of it decomposes, well then multiply that by 0.0033%. So that's 0.0033 over 100. And that'll give you the amount of NO2 lost. So if I were to, well, let's write the equation. So it was 2 NO2 in equilibrium with, looks like 2 NO plus oxygen. All of these are gases. So if I were to set up my table, initially this is 1 molar, and these are zeros. The change, so this is going to decrease by, we'll call it 2x, and these will increase by 2x and x. And yeah, 1 minus 2x, whatever that is, it's still probably going to be approximately 1, considering how small the percent decomposition is. That's going to be 2x, and that's going to be x. So the amount of nitrogen dioxide that decomposes is 1 molar times this number, which is going to be 1.00 times 0.0033 over 100 is 3.3 times 10 to the negative 5. So 3.3 times 10 to the negative 5 molar worth of NO2 decomposes. In other words, that's the 2x. That's the 2x of NO2 that decomposes. So this is equal to 2x. This is the nitrogen dioxide lost. Okay, and from there you can divide by 2 and solve for x, and plug it in to get your equilibrium concentrations, and then do concentration of nitrogen monoxide squared times concentration of oxygen divided by concentration of nitrogen dioxide squared. 1.00 minus 2x, notice that 3.3 times 10 to the negative 5 is several decimal places down from 1.00. So according to the rounding rules, 1.00 minus this number is still going to round to 2 decimal places, so it's going to round back up to 1.00. And this is actually pretty common for reactions with really low equilibrium constants, where the amount of reactant that is lost or consumed in the reaction is so small that the concentration of the reactant at equilibrium is essentially the same as its concentration at the beginning. But yeah, outside of that, I think you know how to handle the rest of this, so I'm moving on. '56, calculate the value of the equilibrium constant Kp for the reaction given from these equilibrium pressures. Okay, so they gave you the pressures, literally just plug them in. NOCl is 1.2, so 1.2 squared over 0.050 squared, and also you're going to have 0.30 to the 1 in the denominator. They're already equilibrium pressures, so you're good to go. No other calculations needed. 57, when heated, iodine vapor dissociates according to this equation. At 1274 Kelvin, a sample exhibits a partial pressure of I2 of 0.1122 atmospheres and a partial pressure due to monatomic iodine of 0.1378. Determine the value of the equilibrium constant for the decomposition. Okay, so they didn't mention otherwise, so I think it's safe to assume that those are equilibrium pressures that they've given you, in which case this is an easy problem. Yeah, this, again, just plug in those values into your equilibrium expression and you're good to go. 0.1378 squared over 0.1122. 58. A sample of ammonium chloride was heated in a closed container. at equilibrium, the pressure was found to be 1.75 atmospheres for the NH3. What is the value of the equilibrium constant? Okay, so for this, you're going to have to do a little bit of working backwards to figure out. Well, actually no, because the ammonium chloride is solid, so it's not going to count. So yeah, your equilibrium constant is just NH3 to the first power times HCl to the first power. And if the container was empty, then you started off with 0 of both. Okay, let me just write out some quick math here so that you can follow what I'm trying to say. So there's some solid NH4Cl that they put in, and you get NH3 gas plus HCl gas. Okay, so they put some solid NH4Cl, ammonium chloride, into a container. They didn't say there was anything else in that container, so you can reasonably assume it was empty. There was no ammonia or hydrochloric acid gas to begin with. And there was some amount of solid. We don't know how much, but probably a lot. We'll just say an excess amount of solid. Some change happened, so this decreased by, we'll just say it decreased by x, and these each increased by x, and so at the end you're at 1.75 ATMs for NH3, which must mean then that you're also at 1.75 ATMs for HCl as well. They were in atmospheres, right? Yeah. Okay. And from there, you don't even need to know this, but it's still going to be some excess amount. So, yeah, just your equilibrium constant is going to be 1.75 times 1.75, and you don't have to divide by anything because that's a solid. And we're good to go. Okay, what about 59? At a temperature of 60 degrees Celsius, the vapor pressure of water is 0.196 atmospheres. What is the value of the equilibrium constant Kp for the vaporization equilibrium at 60 degrees Celsius? This works out exactly the same way as it did. Well, actually, no, it's simple. It's 0.196 because it's the pressure raised to the first power over nothing. There's nothing to divide by because the reactant side is just liquid water. There you go. We did something similar to this earlier where we had to look up the vapor pressure ourselves. In this problem, they just gave us the vapor pressure. Okay. Let's take a look at this. So I don't think I'm going to go over this, but this is a good exercise for you just to practice working with your ice tables. This is a good practice exercise for you. So basically just complete the chart. Fill in the blanks. They fill in some of the blanks for you, and based off of those, you have to fill in the rest. That's really all there is to it. Okay, I'll do part B. I'll do part B just so that we can be clear on what it is they want you to do. So they've given us for part B, there's 4 NH3 plus 3O2 in equilibrium with 2N2 and 6H2O. All of these are in the gas phase. Okay, and we've got your initial change, and they don't, wait. No, it's just the changes. Okay, it's just the changes that they've listed over here. So they want the changes expressed in terms of variables and then expressed again in terms of actual quantities. Okay, that's all there is to it. So they've given us for oxygen, the change is, I'm guessing that was supposed to say minus 3x, but unless I'm reading it incorrectly, all I see is 3x there. Assuming this reaction goes forward, the change is minus 3x, and they say that's equivalent to 0.24 molars for their particular experiment. Okay, fill in the rest of the blanks. Easy enough to do. So first I would do it in terms of variables. So if the oxygen decreases by 3x, then the ammonia would also decrease by 4x. The nitrogen would increase by 2x. The water would increase by 6x. So let's see, 0.24 is equivalent to 3x, so x is 0.08 essentially. So that would make this 0.32 molar. That would make this 0.16 molar. And that would make this 0.48 molar. I think I did that right. Let's see. Double and okay, yeah. So that's basically what they want you to do. And yeah, I'll put it up on the screen again so that you can look at it, take a screenshot, or pause the video, or whatever it is you want to do. And I think there might be another one just like it on the next page. Okay, yeah, and here's another one just like it in case you feel like you need more practice. It's a simple enough exercise, so it's easy to just kind of skip over it and go, oh, this is easy, I already know how to do it. But if you don't practice it, it doesn't become instinctual, it doesn't become natural, and if it doesn't become natural, then you have to exert mental effort every time you have to do this, which means, like I said earlier, you'll be too mentally exhausted when you come to the tougher problems. So yeah, practicing the easier parts of problems is a valid study strategy. Just because it's easy doesn't mean it's not worth studying. Anyway, moving on. 62 says, why are there no changes specified for nickel in exercise 1360 part F? What property of nickel does change? Okay, let's go back to 60 and see. So 60 part F. Okay, that's the bottom one. So they don't have any changes listed because it's a solid. There's not going to be a change in its pressure because, well, pressures are for gases. Nickel is not a gas here, so yeah, that's why they're not listing changes. There is something that changes, which is the number of moles of nickel. But that is neither a concentration nor a pressure, so yeah, that's why it's left out. Okay. And I'm guessing 63 is in the same vein. 64. Analysis of the gases in a sealed reaction vessel containing ammonia, nitrogen, and hydrogen at equilibrium at 400 degrees Celsius established the concentration of nitrogen to be 1.2 molar and the concentration of hydrogen to be 0.24 molar. Calculate the equilibrium molar concentration of NH3. Okay, this one is actually really easy. You don't even need to set up a rice table for this one. They've already given you 2 out of 3 equilibrium concentrations, and they've given you the equilibrium constant, so you can solve for the missing equilibrium concentration. Not that hard to do at all. So they give us NH3 is the product this time, so Kc at equilibrium is going to be NH3 final squared over N2 final times H2 final cubed. We've seen this enough times that maybe some of you have memorized it now. And they've already given us the final concentrations, so we can just plug them in. Kc was equal to 0.50, they said, equals, we don't know NH3 final yet, that's what we're solving for. But they did give us nitrogen is 1.2 molar, and hydrogen was 0.24 molar, so 0.24 cubed. Multiply the 1.2, multiply 0.24 cubed, and then take the square root and you're good to go. So 0.50 times 1.2 is 0.60. Multiply that by 0.24 cubed, and that's about 8.3 times 10 to the negative 3. So I've got, I guess I'll continue here, 8.3 times 10 to the negative 3 equals final concentration of ammonia squared. Square root both sides, and we get 0.091. 0.091 molar equals concentration of ammonia final. It's very easy for students to get into the habit of always use a rice table or always just plug in the concentrations directly. So you can make these problems a lot harder for yourself if you don't remember the fact that equilibrium constants are based on the concentrations or pressures at the end of the reaction, the final concentrations and pressures. Be very, very careful about that stuff. At the risk of sounding like a broken record, I repeat it yet again. Okay, and I guess that's it for that set. 65, calculate the number of moles of HI that are at equilibrium with 1.25 moles of H2 and 1.25 moles of I2 in a 5-liter flask at 448 degrees Celsius. So they gave you the moles and they gave you the liters, which means you can calculate the molarities. And then using those molarities, you can... Those are the final molarities, so you can plug them in just like we did with the last problem and solve for the molarity of HI. And then they asked you for the moles of HI. So use the 5-liter volume multiplied by the molarity of HI to get the moles back again. Okay, and if you try to take a shortcut and not convert the moles to molarities, will that change the answer? Let's see. If I... Yeah, actually I think it will. Let me try that real quick. So 50.2 times, and then, okay, take that versus 1.25 over 5, and then square that, and then square root, and Oh, you get the same result either way. Okay, interesting. I'm going to have to find some sort of algebraic proof for why this works and figure out when it does work and when it doesn't. But apparently you can sort of cheat through this one. Okay, so that's 65. You know how to do it. 66, what is the pressure of bromine monochloride in an equilibrium mixture if the pressure of Cl2 in the mixture is 0.115. Okay, so they called it an equilibrium mixture, therefore everything in there is already at equilibrium. So, yeah, again, same thing. They gave you the equilibrium pressures of 2 of the 3 compounds, and they gave you the equilibrium constant, so you can get the equilibrium pressure of the missing one. 67 looks like more of the same. Okay, let's take a look at what we have next. So, cobalt metal can be prepared by reducing the cobalt-2 oxide with carbon monoxide. What concentration of carbon monoxide remains in an equilibrium mixture with carbon dioxide concentration 0.1 molar? Okay, well, the cobalt and the cobalt-2 oxide don't count, so your equilibrium constant is equal to equilibrium concentration of CO2 over equilibrium concentration of CO. You've already got 2 of those numbers, you can solve for the third, so more of the same. Okay, 69. Carbon reacts with water vapor at elevated temperatures. Assuming a reaction mixture initially contains only reactants, what is the concentration of carbon monoxide in an equilibrium mixture with water vapor concentration of 0.5 molar at 1,000 degrees Celsius? Okay, so they're saying the final concentration of the water vapor is 0.5 molar, and it started out as just water vapor and solid carbon. Okay, so you might have to do some ice table backtracking here. Let's at least try and set this one up. So we've got carbon solid, which isn't really going to count towards the equilibrium anyway, and water vapor with carbon monoxide and hydrogen. Okay, and we know Kc is equal to 0.2. So, they said it's initially only reactants, so initially we only have reactants. So initially some unknown amount, let's just call it big C for concentration. And the equilibrium mixture has a water vapor concentration of 0.5 molar. Whatever the water vapor started at, it ended with 0.500, so at the very least we know that this C value is bigger than 0.5. Okay, and these started at 0. Oh, okay, this isn't too bad. So, since the balancing coefficients are all 1 to 1 to 1 to 1, this is going to decrease by x. These are each going to increase by x, so their final concentrations are going to be x and x, and your Q equals Kc at equilibrium, so 0.2, that's going to be x times x, which is x squared, over 0.5. And yeah, multiply 0.2 by 0.5, that's going to be 0.1 equals x squared, and then if you take the square root of that, square root of 0.1 rounded to 1 sig fig is 0.3 apparently. So x is about 0.3 molar. Those are the concentrations of carbon monoxide and hydrogen in there. And was that all they wanted? Yeah, they wanted the concentration of carbon monoxide, which also equals the concentration of hydrogen that we didn't want. And if you wanted to calculate the initial concentration of water vapor, you could do that. Now that you know x is 0.3, you know that 0.5 molar is the same as initial plus change, so C plus negative x is equal to 0.500. That's 0.3, so add 0.3 to both sides. So initially we started with 0.8 molar of water vapor. They didn't ask for that, but you could do it if they did. It's not that bad. Okay, so that was 69. 70, we've got sodium sulfate 10 hydrate. Oh wow, that's cheap. They couldn't call it decahydrate. They went the cheap route. Okay. Because expecting students to know the deca prefix for 10 is just asking too much. Okay, I see your game. I see your game. Oh, whoever wrote these problems, well, whoever wrote this problem specifically, better wish they never reveal that fact to me, or else they're gonna get an earful. Oh, look, and they did it again with 71. Calcium chloride 6-hydrate. It's supposed to be hexahydrate. I don't think most people would be confused if you used hexahydrate. I mean, hexa is pretty common. It's not hard to find people who associate it with the number 6, but I digress. Anyway, sodium sulfate decahydrate dehydrates according to the equation given. Okay, so we've got a solid and a gas. So the equilibrium constant is just going to be the final gas concentration raised to the 10th power. What is the pressure of water vapor at equilibrium with a mixture of the hydrate and the anhydrous sodium sulfate? And they missed a 2 on that sodium sulfate before the question mark. It should be Na2SO4. What's the pressure? So yeah, just take the 10th root and take the 10th root of the Kp and you should be good to go. In this case, at equilibrium, Kp is equal to pressure of H2O final to the 10th power. And there's nothing to divide by because everything else is solid in this reaction. So at equilibrium, they said, what's the pressure of the water vapor at equilibrium? Well, just take the 10th root of Kp. So if it's at equilibrium, you've got 4.08 times 10 to the negative 25 equals our desired pressure to the 10th power. Take the 10th root. If you don't know how to do that on your calculator, you just raise everything to the 1 over 10. So final pressure of water vapor when you're at equilibrium is 4.08 times 10 to the negative 25. Plug that into your calculator, and then raise it to the 1/10. Raise it to the 1 over 10, and that's how you take the 10th root. And yeah, the rest is just calculator work. You can plug in the number and find out the result for yourself. And I guess it'll have 3 sig figs. And it'll be in atmospheres. We typically calculate Kp from atmospheres, not torrs or any other pressure units. 71 looks like it's virtually the same thing, except you're taking a 6th root instead of a 10th. But yeah, it's effectively the same. 72, a student solved the following problem and found the equilibrium concentrations to be those numbers. How could this student check the work without reworking the problem? Oh, just plug them in and see if their ratios give you K equals 4.32 or something close to that. So yeah, just plug in, what is that? SO3 squared over SO2 squared and O2 to the first power. Just do that division and see if you get 4.32 or reasonably close to 4.32, and that'll prove that you did it right. If you calculate equilibrium concentrations based off of initial concentrations and the equilibrium constant, we did do an example of that earlier with, let me see if I can find it. I mean, I know I can find it. It's got to be somewhere here. Yeah, with this, right? We calculated X, we calculated what the equilibrium concentrations would be, and then we just plugged them in to check. And yeah, they work out to 18, which is about right. The equilibrium constant should be 17, but, you know, rounding errors and stuff like that. So that's not anything too hard to do. Let's take a look at the next set. See if there's anything worth our while here. 73 looks like it's the same as 72, so skip. We already described how to do it. 74. Assume that the change in concentration of N2O4 is small enough to be neglected in the following problem. Oh, that is something that we're going to be doing a lot of in the next video, actually. Assuming that the amount of a reactant that's used is negligible. Simplifies your calculations a lot, and oftentimes you can get away with it, so why not? Why not avoid the quadratic formula? Anyway, it says calculate the equilibrium concentration of both species in 1 liter of a solution prepared from 0.129 moles of N2O4 with chloroform as the solvent. Okay, chloroform being the solvent is an interesting detail, but not relevant to what we have to do. It doesn't change our solution process in any way. Okay, I'll just go over the setup. So, we've got N2O4 decomposing into 2NO2. And let's see, we start with 0.129 moles of N2O4 in 1 liter of solution, so that's 0.129 molar. So it starts as 0.129 molar, and this starts at 0. This decreases by x, this increases by 2x, and at the end, at equilibrium, I should probably label these rows. At equilibrium, you've got 0.129 minus x, and you've got 2x. And we know the equilibrium constant is 1.07 times 10 to the negative 5. So that's your k value. Let's see. So if I use the equilibrium concentrations, that's going to be NO2 squared over N2O4, so that's going to be 2x squared over N2O4 is, normally you would write 0.129 minus x, and that's to the first power. Now, if you square this, you're going to get 4x squared, and if you multiply this over to the left-hand side, you're going to get, well, you're going to get a quadratic equation, right? You're going to have an x squared somewhere, and you're going to have an x somewhere, and you're going to have a constant. And how much fun was it when we used the quadratic equation earlier? Not that fun, right? Do you really want to go through this if you don't have to? Sometimes we'll have to, so it's inevitable that you'll need to use the quadratic formula every now and then, but there are many cases where you can avoid that, and they're telling us this is one of those cases. So they're telling us assume x is really small, is negligibly small in comparison to the initial concentration of N2O4. Not something we haven't seen before. In fact, we saw this earlier with, where was it? With this, right? When we were looking at this, we got 2x is 3.3 times 10 to the negative 5. If you subtract that from 1.00, then you're going to get 0.99 something, and you're going to have to round it to 2 decimal places anyway, so it rounds back up to 1. So yes, it is possible to get x's that are so small in comparison to what you're adding them to or subtracting them from that they might as well not even be there. They might as well be neglected. And that's what we're going to do here. 0.129 minus x is approximately still equal to 0.129. They have reason to believe that the x is going to be incredibly small. And you can predict that based off of the equilibrium constant. 1.07 times 10 to the negative 5 is a rather small number. You're not going to get a lot of product when k is so much less than 1. So that's part of the reason why we can justify this. We'll talk about this some more in the next video. We'll develop a rule of thumb where you can make the judgment, because sometimes you have close cases where it's not so easy to justify this assumption. But yeah, if we do that, then this makes the math so much easier, because now it's 1.07 times 10 to the negative 5 equals, I'm going to go ahead and square that, so that's going to be 4x squared over 0.129. Oh, look, and now all I have to do is multiply by 0.129 and divide by 4 and take the square root, and I got my x. And then I guess multiply that by 2 to get 2x if that was what they wanted. What did they want? Yeah, they said calculate the equilibrium concentration. So once we get x, multiply it by 2, and that'll give you 2x, and that's the equilibrium concentration of nitrogen dioxide. Okay. Let's see what else we've got. 70. Oh, and I guess part B of 74 says confirm that the change is small enough to be neglected. So, very easy to confirm. If you calculate based on the idea that the x can be neglected from 0.129 minus x for the N2O4, then whatever you get out of that calculation, if you go back and plug it in and check, and see if it does equal the K value that we were given, then that means that you got away with it. It works. But if you calculate X using this assumption and you plug it back in and the K value you get is noticeably different from 1.07 times 10 to the negative 5, then that means the assumption you made was not very valid, and you're going to have to go back to the drawing board and do things the hard way. Okay, 75, basically the same. 76, basically the same. We are nearing the end. Is there anything here worthwhile? 77, what are all concentrations after a mixture that contains 1 molar water vapor and 1 molar dichlorine oxide, I guess, comes to equilibrium at 25 degrees Celsius. They've given Kc. Okay, that one isn't too hard to do. Set up your rice table and plug in your equilibrium concentrations, which will have x's in them, and solve for x and find the equilibrium concentrations after plugging in the x value that you calculated. Nothing too new, so let's move on. 78, virtually the same as 77, it looks like. 79, calculate the number of grams that are at equilibrium, and they've given you moles and grams. Okay, so here you just have to calculate molar masses and do conversions, but outside of that, nothing too weird. You just have to be careful about what they're asking for and what they're giving. And it looks like they didn't give you the volume. And based on that calculation I did earlier, maybe the volume doesn't matter. Maybe you can treat 1.25 moles as being the same as 1.25 molar. Oh yeah, and it's the same reaction, so I know for sure that at least for that reaction it works. So just assume it's a 1 liter container and work it out. It should be fine. And convert once you've found the molarity of HI at equilibrium. Multiply it back by your assumed 1 liter to get moles, and then multiply by the molar mass to get your grams. Nothing too strange there. 80, butane exists as 2 isomers, N-butane and isobutane. Okay. What is the pressure of isobutane in a container of the 2 isomers at equilibrium with a total pressure of 1.22 atmospheres? Okay, total pressure is 1.22. So let's map out the math for this one. So I'm just going to write, well, what am I going to write? So isobutane is the product. I'm just going to abbreviate it iso. So Kp equals, and I just have 1 molecule of each, so they're both to the first power. So isobutane is the product, so concentration of iso, or I should say pressure of iso over pressure of N-butane. If Kp is 2.5 at 25 degrees Celsius, then I can say 2.5 equals pressure of isobutane over pressure of N-butane, and we know that the total pressure is 1.22, so P iso plus P N is equal to 1.22, and from there you can just do a simple substitution and solve. So for example, I can write P iso is equal to 1.22 minus P of N-butane, and then just take that and plug it in over here. You'd get 2.5 equals 1.22 minus Pn over Pn. Multiply Pn over to both sides. Okay, I think this one will actually be rather quick to work out. 2.5 Pn, so I guess I'll continue it down here. 2.5 Pn equals 1.22 minus Pn. Add Pn to both sides. 3.5 Pn equals 1.22. Divide by 3.5, you've got Pn. 1.22 minus your value of Pn that you calculate from here gives you P iso, and you're done. Not too bad if you're on top of your algebra skills. Not too bad at all. 81. What is the minimum mass of calcium carbonate required to establish equilibrium at a certain temperature in a 6.50 liter container if the equilibrium constant Kc is 0.50 for the decomposition reaction of calcium carbonate at that temperature? Oh, okay. So, yeah, because the calcium carbonate is a solid and doesn't affect the equilibrium, you're going to want to have an excess amount in order to reach equilibrium in the first place. If you run out of calcium carbonate before you create enough carbon dioxide to create the pressure needed to reach the equilibrium constant, then you won't. You'll just reach some maximum concentration / pressure of CO2, and everything will stop, even if that concentration / pressure is not going to give you an equilibrium constant of 0.5. And come to think of it, since carbon dioxide is the only product that can have a concentration, the equilibrium concentration is 0.50 molar. So yeah, you would need enough calcium carbonate to produce 0.50 molar carbon dioxide in a 6.5 liter container. That means that you would need, let's see, 0.50 molar times 6.5. You would need about 3.25 moles, or I guess 3.3 moles if you round to 2 sig figs. So you need about 3.3 moles of calcium carbonate. Use the molar mass to get how many grams of calcium carbonate that is. Okay, that's not terrible. If you use less than that amount, if you use less than 3.3 moles of calcium carbonate, then your reaction quotient will be stuck somewhere below 0.50, and it'll want to go forward, but it can't because it's run out of material. So yeah, limiting reactants can affect equilibrium. That's the takeaway from that problem. Only a few more sets to go. 82. Calculate the moles of each component in the final mixture. Been there, done that. 83. The following equilibrium partial pressures are measured for all three of them. Okay. How will the partial pressures change if hydrogen is removed? Okay, so that's more Le Chatelier. We've seen that. And part B wants you to calculate the new partial pressures after hydrogen is removed. Okay, so that's something you can do. It's not that bad. 84 looks like pretty much the same thing, right? On analysis, an equilibrium mixture of the substances present was found to contain 0.2 moles of CO, 0.3 of vapor, and 0.9 of H2 in a liter. How many moles were there in the equilibrium mixture? That's a simple calculation. What else do we have? Part B. Okay, yeah, these are all things that you can calculate with ice tables, and I guess this helps you just kind of put concrete numbers to what's going on with Le Chatelier. So yeah, I'll pass on that. I think we're about done. I don't think there's much else to cover. I mean, we'll see more equilibrium in the next video, so this isn't over. 85 antimony pentachloride decomposes according to this equation. Okay, so very reminiscent of PCl5 decomposition. How many grams of each will be found if the mixture is transferred into a 2-liter flask? It started in a 5-liter flask and you transfer it to a 2-liter. Okay, so you'd recalculate the new concentrations after you've changed the volume. So you get the concentrations in the 5-liter flask, convert to the number of moles, and then divide that by the new 2-liter volume to get the new molarities, and then set up a new ice table and calculate what the final concentrations will be in the new conditions and work your way towards grams of each substance. You already have all the necessary knowledge to do that. 86. What's the expression for the equilibrium constant? That's just, you know, the formula. NH3 to the 4th times O2 to the 7th over NO2 to the 4th, and also over H2O to the 6th. Nothing new there. Part B. How must the concentration of NH3 change to reach equilibrium if the reaction quotient is less than the equilibrium constant? We've already talked about that. C is Le Chatelier. We've talked about that. D is not Le Chatelier. It's an ice table problem where they give you one of the change values in torrs. I would convert that to atmospheres. And actually then I'd probably convert that to molarity as well because they gave you Kc, I think. Let's see. 11, 10. If the change in the pressure of NO2 is 28 torrs as a mixture of the 4 gases reaches equilibrium, how much will the pressure of oxygen change? Okay, yeah, it's even easier than I thought. It's based on relative change. If the change in NO2 is 28, well, the change in NO2 at any given time, you can describe it as 4x, while the change in O2 is 7x, plus or minus, depending on which way you're going, whether you're going right or left. And yeah, if the change in NO2 is 28, so 4x is 28, x is 7, which means the change in oxygen is 7x. 7 times 7 is 49 torrs. Okay, that's way easier than what I thought it would be. And here's the last set. Let's see if there's anything interesting here. If there is not, then we'll just wrap things up. The binding of oxygen by hemoglobin. Let's see, partially regulated by concentration of hydronium. We'll talk about hydronium in the next video. Let's see. So, although the equilibrium is complicated, it can be summarized as that equation. Write the equilibrium constant. We know how to do that. Explain why the production of lactic acid and carbon dioxide in a muscle during exertion stimulates release of oxygen from the oxyhemoglobin in the blood passing through the muscle. Stimulates release of oxygen. Okay, so in other words, drives that equilibrium to the right. Well, because if you're producing lactic acid and CO2, you're increasing the concentration of CO2, which is a reactant, so that's just Le Chatelier. Increasing concentrations of products drives the reaction towards, increasing the concentrations of reactants drives the reaction towards the right, towards making products. Okay, so that's pretty simple. 88, liquid dinitrogen trioxide is dark blue at low temperatures, but the color fades and becomes greenish at higher temperatures. Sounds like Le Chatelier to me. And calculate the equilibrium partial pressures. Did they give you the... Yeah, they gave you the Kp value, so you can do that. It's nothing too different. It's just a wordier version of problems we've already done. 89. We've got equilibrium concentrations, which will allow us to calculate an equilibrium constant. Okay, and then they change the nitrogen concentration and they want you to adjust the hydrogen so that your reaction quotient remains the same. That is, remains equal to K. Okay, yeah, you can do that. You already have all the necessary knowledge for that. Okay, well, I guess that's it then. I don't think we need to go over anything else. So yeah, plan for next time, as I've mentioned, is more equilibrium. We're going to dig into acids and bases. We've talked about acids and bases before, but now we're going to talk about them in some more depth. Now that we know some equilibrium concepts, we can really take a hard look at how acids and bases function, because most acids and bases, they don't dissociate completely. They do establish some sort of equilibrium. So knowledge of equilibrium was necessary before we could talk in depth about acid-base concepts. But that's coming up next. So yeah, practice your equilibrium, get used to ice tables and stuff like that. Make sure you understand the ideas behind Le Chatelier's principle. As an added bonus, it might be worthwhile to understand the math behind Le Chatelier's principle. Even though it's not mandatory, I think it'll help you immensely in just developing your intuition. And yeah, I guess that's it for me. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you in the next video.